Let's just make sure. Okay, I think you can hear me now. Oh my goodness, this has been nothing but technical issues all morning. Hopefully you guys can see me here anytime soon. My microphone broke. If you see this very strange like apparatus, this clunk of stuff sitting on my lapel here, it's duct tape. I have literally had everything fall apart on me this morning. This is my mic clip. Anybody see this? I don't know if you can see this thing. This is my mic clip. It dingle, dingle, dingle. Did anybody see it dongling like this? This is terrible. So I'm scrambling, going, oh my gosh, I'm already late. And now as I'm pinning it on me, it just falls apart. And I'm thinking, what am I going to do? I tried Scotch tape. I tried to like tuck it in, various parts to have it hang on. Nothing. I finally had to run out and grab some duct tape from luckily I run a studio, right? So I duct tape. If you can't fix it, duck it is the terminology. So that's what this nasty little spider thing looks like on my chest right here. If you see this nasty little thing of glob of stuff, it's duct tape, where it's actually duct tape my mic to my shirt. So if things go a little wonky today and my audio falls or my mic falls off my shirt, bear with me. I do have an extra microphone that I've put up just in case, so I can turn it up and use a handheld. But yes, wonderful world of DIY classes. So good. I'm glad everybody is telling me they see me. And yeah, you've had days like that. Thanks, Leah. Oh, goodness. I don't know if you guys can see the sweat. Women aren't supposed to, we're supposed to glow, right? Well, whew, I'm glowing profusely this morning because I'm trying to get online for you all. Okay, so good. Everybody sees me. Try super glue. No, I am not going to try super glue, Andrew. My goodness. Wouldn't be able to get this thing off for a month without removing skin. Grabs popcorn. Yeah, I know. I can be very entertaining when things don't work out. Luckily, I have a decent sense of humor, and so hopefully you're getting to laugh at me a little bit, because I laugh at myself all the time. So please turn up the volume if you can. Okay, yes, I will. Let me turn up the mic. Yeah, and you might get that. There may be some issues with my mic on and off today, so don't be shy. I just turned it up a little bit. Tell me if that's better. I'm trying to look at my mic levels here. If I distort, let me know. I'm going to turn it up a little bit here. Check, check, check. Okay, but yeah, my mic is it's flopping a little bit, so pardon. I got to get a new microphone. Okay, so it looks like everybody says it's all right. How do you do the screen background like this where we can see you, where we can also see you? I have a cute little tool I use. Anybody want to have a cute little lesson in this real fast? I did this for someone the other day. See, my cell phone, you may think, well, what is the cell phone for? Well, I'll show you. I have something called a Sling Box, or Sling Studio rather, and anybody who knows what that is, let me find the app that works it. Come on, where are you? There you are. The Sling Studio is kind of like a little mini computer in of itself. And what's neat about the Sling Studio is that it takes production cameras like the one you see here, but it also takes inputs from my cell phone. It can take it, as long as you have the app, you can actually use it. So if I do this, for example, whoops, let me make sure that you can't hear that microphone. I don't want you to hear my cell phone microphone. So if I do this, for example, watch this, you'll love this. Oh my goodness, now you're going to see two of me. My background is now my cell phone. So hi, there I am. Here's my green screen, guys. I have to get out of the way. Get out of the way of my production camera. And you can see my green screen right here. You can see my messy studio and my lights. And you can even see you. This is you guys as I walk up to my rig. So you're getting a little tour, an impromptu tour of what my studio's like. Messy, okay, so, and yes, I am macabre. I like skulls. I like anything to do with Halloween. So I have friends that give me skulls and I do collect them. It doesn't make me creepy. It just means I like Halloween. And yeah, so here's my studio, and sorry about the shaky camera, but it's one of the cool things about the Sling Studio. Oh, and then here's my controller for the Sling Studio, and I can change cameras back and forth. Whoops, I'm probably in the way. Let me get out of the production camera. Actually, I can probably just do, I can remove myself from the program. Hold on. Let me do that. Make it easier. Remove from all. There we go. Now I disappeared. So now you can see better. Here's, whoops. Here's the setup for the Sling Studio. The Sling Studio itself is just this little box right here, believe it or not. Just this tiny little box, and then it goes into one of my computers down here, where I trick the system to think that it's a webcam, and so that's how I do that. So here's my production camera. For those of you who've never seen any way how I run this, here's my background computer that I have feeding into that as well, and then yeah, and then this is my setup. So this is the way I see you. I stand here, I stand here and I read off of my big TV. I read all of your comments and stuff. Pretty cool, huh? So let me get rid of that and go back to, whoops, yeah, there we go. So I'm going to go back to my main production camera now. There I am. Okay, and I'm going to kill the cell phone feed. So hopefully that gives you guys a little bit of a ridiculous little tour that I wasn't expecting to give you, but it's already been such a crazy morning, so why not? So you must have quite an, yes, I've got like 3 power conditioners. A lot of the gear that you saw, I'm sorry, I'm answering John Ratnaswamy. Hi there, I haven't seen you in a long time. Good to see you. John, you've been with me since like 2018, maybe 2016. It's been a long time. I remember meeting you on Twitter. Anyway, when I went to grad school and did all my physics, I had to keep myself sane, and I kept myself sane by doing music, because I was an artist before I was a physicist. And the only way I could get through grad school is to be able to play music and do music for other people. So all of that gear you saw was stuff I literally built up and bought while I was a grad student and doing records for other people. And it's just stayed with me, all of this gear. I wish I'd use it more now, but the Space Weather Woman stuff has really taken over my life, so I don't have much time for music anymore, sadly. I wish I could get back to it. But yeah, so I ended up having tons and tons of power conditioners and old computers and stuff like that have really translated well to this kind of work, and it keeps things going pretty smoothly for the most part. So thanks for noticing. Yes. Very nice living room. That's actually my studio. It's not even a living room, but it is a living space. I do all of my work in here. So. Oh, good, Joe. You have a green screen to do interviews. It's getting better. Oh, and if any of you haven't checked it out and you have Macs, check out an app called literally MMHMM, I think. They're doing beta testing right now, and they've got some really neat tools for those of us who are doing green screen work and want to do video conferencing better. I am waiting for them to have a Windows version, because I don't have the newest Mac application or Mac operating system to be a beta tester for them. But it's a neat kind of, looks like some neat software coming out of them. So if you get a chance, take a look at them. I'm pretty impressed, and I am not being paid by them. So that was just an honest and kind of look-see, hey, check out this latest tech gadget that's really got my attention. Because it can help with stuff like this if you want to do this and you don't necessarily have all the tools that you need to be able to do it. So, okay, sorry for the little, divergent thing there, but that was kind of fun. Hi, sweetie, you're doing great. Teacher loving you from Israel. Oh, thank you. Thank you. Is it Adiel? Thank you so much. That was so kind of you. A musician, yes, has the correct frequency connection with all above us. Yeah, music is the universal language. So yeah, I'm hoping that being an artist helps me be a better teacher, of physics as well. I think because it's all connected. It's all about language. And if we get the language right, we can teach each other anything. What program did she say? Sadly, MM as in M as in Mary, and HMM. So MMHMM. Why they decided to call it other than it being an English way of saying yes, or I get you. I don't know. I don't know if that is going to help them or hurt them, but nonetheless, you can actually look them up on YouTube. They've got some videos right now, but they're doing beta testing, and they're doing a big launch of this software, this app, only on Mac right now. We're waiting for Windows, but it might be really cool. Can you sing? Yes, I do. I sing quite often. I have lots of music, and eventually I will put some out. But yes, I do sing. I sing, play guitar, play piano, play mandolin, play anything that doesn't bite me. I will play, or at least I'll try to play. So yeah, I did audio engineering, and I also produce records for people. So let's see. Okay, yeah, exactly, Mandy, you got it. So, okay, guys, today, if we can get started on this, today I'm going to begin the course on coronal holes and the sources of the solar wind. If you were with me last month, near the end of the course, I paused and said, hey guys, do you want me to continue and talk about neutron monitors and finish that course off, or do you want me to wait? Some of you said wait, some of you said continue. But as it turned out, with the Patreon group that I have and just other comments that I've gotten from people, they said, you know what, why don't you just move in? We're dying for you to get to new subjects, so why don't you just start the new subject? Don't do another radiation storm course. Let's get into coronal holes so that we can get into some of the other subjects people want me to talk about. One of those, for example, is how geomagnetic storms work. So I promised several people, and I guess I could call you out by name. Let me check to make sure no one said don't call me out by name, but I need to, hold on a second, let me just see. I'm just checking in my Patreon feed at the moment. So give me just a second while I do that. But what I actually do, uh-oh, I think my microphone may be going out on me. Hopefully you're there. Did my mic go out? Hopefully not. Hopefully it's still okay. Let me check. So Jack in particular asked me to go into a little bit about geomagnetic storms, because as we've learned so much about space weather phenomena, we spent so much time on space weather phenomena, but we haven't spent any time on what happens when you actually hit Earth. And I know that has been purposeful, and it's actually, if for those of you who follow me, and the reason why I'm doing all these courses here on YouTube is because I'm trying to get courses ready for Millersville University, which we're actually teaching a graduate level curriculum right now in space weather communication and broadcasting. And so I've separated out, I have two main courses that I'm teaching, and I'm separating them out. One is teaching just the phenomena of space weather, and then the other one is teaching the effects once these things hit Earth. So what that means is that I've done a whole, probably, oh my gosh, almost a year worth of courses here on YouTube and on Patreon, basically just about space weather phenomena, right? Just the stuff that comes from the sun. And this is the last of the grouping of them. And then we will go into detail into what happens when this stuff hits Earth. But I did promise Jack today that I would talk a bit about that. So I probably will wait to the end to talk about the geomagnetic storm stuff, but I do have some charts for you, Jack, that I will go ahead and tack on at the end of this lecture about geomagnetic storms, and then just know that that's just going to be a primer, because we're going to get into that more as I get through the coronal hole, this coronal hole and solar wind talk. Okay. Once I get through this subject, then we'll move on to the effects at Earth, and I will go into great detail, probably more detail than you want to know, about geomagnetic storms and substorms and the difference between the two and what matters, how they affect different aspects at Earth, including astronauts, and obviously space tourism and all that kind of stuff, and people on the ground. So just know that's coming, and like I said, if you want to stick around to the end, then you can see me talk about that. Give you a little bit of a primer, a little heads up on that. So before I begin officially, I want to thank everyone behind me. I think I go over here. Let me do this, let me put this in presentation mode. Hopefully you guys see it. Yeah, it looks like it. Okay. So I want to thank my VIP committee, the steering committee. You guys have been keeping me sane and making sure I am staying on the right track. You guys help me steer the ship, and you are helping determine the course, the agenda for the courses and the curriculum for the courses I'm teaching at Millersville. And so I can't thank you enough. I wish more of you would join me actually during our VIP committee meetings, but I have a nice, really wonderful core group of people, including Jerry, Lourdes, Greg sometimes, Notani, Keith, Mike, Stacy, sometimes Bernie, and Nikki sometimes, and I'm hoping Deepak pretty soon, and hopefully Nathan from NSS North Houston Space Society. Hopefully you guys will join me a little bit more often, but I do really appreciate the core group of people. As a matter of fact, I do have probably several of you who will text me. I do have my phone, so text me if my audio goes out or anything like that, or give me a call, because you guys have my number and everything if need to. Okay, good. As a matter of fact, Jerry just contacted me now. Let me see what he says. Thank you, Jerry. I have your 6 in the chat room for any tech issues. Wonderful. Thank you so much. So yes, I do have my phone with me. And I am worried about my mic. And then on top of that, I've got the MiniCourse page. Whoops, I know I need to say, I'll stay on this side. I have all my MiniCourse patrons. If you do not see your name up here, I did update it just a little while ago. If you do not see your name up here, feel free to drop me an email or a slap on the wrist. I'm trying to get this updated. I'm not always the best, but you guys, I can't thank you enough for everything that you do. You help make these courses possible, and you inspire me in ways that you have just no idea. You also are the reason why I teach what I teach. So please keep giving me the suggestions. Please keep telling me, when you need me to move on. All of that stuff. You guys are just you're the heart and soul of this. So much appreciated. Okay, and with that, oh, Notani, good to see you here. That's awesome. And Susie Cat, good to see you as well. I'm so glad you're here with me from Scotland. What's your number? That's funny. If you're a VIP member, you actually get my phone number, but you have to be very, very careful with it. And you have to be serious if you're a VIP member. People are there to help me push this field forward, and they are invaluable, and they take it as seriously as I do, and I'm so eternally grateful for it. So, okay. So, let's see, are there any other questions? Pimp Daddy Smooth, I love this channel when I catch it. Oh, I'm so glad you're here then. Great. Fantastic. Definitely ask questions as we go along, okay? And Blue Star, hi Tamitha from Texas. Wonderful. Thanks, guys. Much appreciated. Okay, so let's get moving and enjoy the new topic. My goodness, I finally get to go into something new. So I'm going to stand over here and remind you all that we've talked about solar flares. So any of you who have not seen my other presentations, my other mini courses, these are the phenomena that we've gone over thus far. We've gone over solar flares, and those are different than solar storms, okay? And I'm not going to, I have movies for these, but I'm not going to play the movies because you can catch it in half a dozen of my other courses. We've gone over these in very grave detail, or great detail, and then we also just finished the course on solar radiation storms as well as cosmic rays. Okay, so those, I call this solar radiation storms, but there's also another kind of radiation storm that doesn't come from our star, it comes from other stars. And those are cosmic rays, but it kind of is very similar in aspects. So I covered them both in the solar radiation storms, and oh my goodness, we are finally down to coronal holes and fast solar wind. And I will answer a question that I've been dying to answer for ages. Is this a hole on the sun? No, it's not. It's not a hole in the sun. The sun is not splitting in two. You can't drive a spaceship through it or anything else like that. You will not get to the core that way. This is simply a dark region in this wavelength of light. Okay? Any of you who've watched, let's say, sunspots and telescopes, one of my other mini courses, you know that scientists look at the sun in many different colors of light. Those are false color images, right? The coloring is really just an indicator for us so that we know what wavelength of light we're looking at the sun in. That tells us which layer of the onion we're looking at. And in certain wavelengths of light, for example, this pink sun, which is 211 angstroms, this pink sun shows us that we are looking at essentially a little bit above the chromosphere as we transition into the corona, and where everything is cool, meaning that it doesn't have a lot of light being emitted in 211 angstroms, that is where a coronal hole is. Okay, we call it a coronal hole because it looks like a hole. It doesn't mean it is a hole. It just means that it's the source of fast solar wind, and it doesn't have a lot of what we call closed magnetic field. And we will talk about this. That's what this course is today. But if I were to look at this sun, this exact same sun in a different wavelength, let's say the red sun, which is 304 angstroms, you would be hard-pressed to find where that coronal hole is, because the sun would be just solid red. You'd look at it and go, where'd the hole go? Well, because in 304 angstroms, the whole sun is lit up. It's emitting light in that wavelength everywhere. So there really isn't a hole at all. Okay, so don't ever worry. Anytime you think when you see the sun in this wavelength, number one, don't get it confused for a sunspot. I've seen that happen even in books. Unfortunately, a book that I'm in confuses an active region for a sunspot for a coronal hole. Ouch. It was actually vice versa. They called a coronal hole an active region. But the other thing is, don't worry, the sun is not about to split apart. It's just cold in this particular wavelength of light, okay? And that's one of the reasons why we tell people, or why us scientists take a look at the sun in all these different wavelengths, is because each wavelength looks at a different layer of the sun, and it tells us something else, something different about what is maybe happening, you know, with the plasma and with everything that's going on in the sun's surface, and the sun's moving just above its surface to a chromosphere, what we call the transition region, and then up even higher into the solar atmosphere. There's all sorts of stuff going on in all of these different layers, and we need these different wavelengths because they probe these different altitudes for us individually, and it helps us understand what is happening, because there's just always so much going on in the sun. So if you need a review of all that stuff, please, I suggest going back to Sunspots and Telescopes, because that's probably the best one to take a look at. That'll tell you all about what we look at when we look at the sun and why we look at the wavelengths we do. So, to remind everyone, what is a plasma? Because you will hear me say plasma, you will not hear me say gas. Okay? Now I'm going to stand over here. Remember that the difference between a solid, liquid, gas, and a plasma is that there are different phases of the same matter, okay? We're used to solid, liquid, gas. Sure, 3 phases of matter, but there is a 4th state, and that's plasma. As you know, solids have a very strong lattice structure, right? Ice, for example. Water is when the lattice structure falls apart, and then the water molecules are kind of free to move. They still kind of are gluey and sticky to each other, but they will hold together, but they can take the shape of any container they're in. Once you're at gas, then the molecules really aren't sticky anymore. They hit each other, but they don't stick, and they can fill any volume, right? They don't really, it doesn't matter what size it is. And of course, we know, from these examples, ice, water, steam, those are very common phases of matter. But you can also go into a different kind of gas, and this is when you actually rip off parts of the atom, right? You're actually ripping the electrons right off the atoms in the gas itself, okay? When you do that, suddenly, instead of having molecules, which they have down here as being these blue molecules, you now rip them off and you have ions and electrons, okay? So you're separating that. And then they're just floating around similar to a gas does, right? In a collisional gas, they're in a collisional plasma, they bang into one another and do exactly what they do in a gas. The difference is, because they're charged positively and negatively, they now see and feel the effects of magnetic and electric forces. So because of that, they will light up. They will move the way, the way the magnetic field tells them to, right? Or they'll move, if you have an electric charge, they'll accelerate, or an electric field, they'll accelerate in that field. They'll slow down, speed up, change direction, all that kind of stuff that a neutral gas will not. So it becomes something that is that you, well, not only does it become something that you see in space a lot, everything in space is basically a plasma. There are no neutral particles in space. But what becomes very interesting is that when you take, and I guess I should back up a little bit before I say this, an example of an ionized gas, or meaning a plasma, that's collisional, is lightning. Okay, these particles are bouncing off each other in the air, but if they're ionized into a plasma, you will get something like lightning, right? And you will get these really ragged jolts of things. The reason why it's so ragged and kind of ratty is because these particles are bouncing off one another and colliding, and so you get these really jagged flows of electricity and energy moving back and forth. In space, it's not quite like that, because in space we have a plasma, but in this case it's collisionless because it's such a vacuum. We have very few particles in the same space, and now they're not even touching one another. They don't bounce into one another anymore. As a matter of fact, the only way one particle knows the other particle is there is through the electric and magnetic fields that connect them. So really, it's kind of, you look at it more with a collisionless gas, you look at it more, I mean collisionless plasma, you look at it more like a spider web, where you have particles kind of think that you have particles kind of on a spider web. And they're not, particles aren't touching each other, but if you shake the spider web over here, the web feels it. It shakes on this side too. So that's how the particles communicate with one another. So suddenly the dynamics of a collisionless plasma become radically different than the dynamics of a collisional plasma. So a collisional plasma, you would have lightning, but with a collisionless plasma, you light it up the same way, you get aurora, smooth, undulating current, patterns that just don't have any ragged edges, because nothing's colliding into one another. It becomes a very soft, gentle ballet between the particles as they get lit up or get energized or whatever it is. And the reason why they bend and swirl and move is literally because that's the direction, or that's the movement of both magnetic and electric fields. Okay? And the reason why I have to bring this up is because when I talk about a plasma in space and near the sun, I'll be talking mainly about a collisionless plasma, especially when we're talking about the solar wind. Okay, we're not talking about a wind that has particles that touch each other at all. We're talking about that spider web, and think of particles that are so far separated from one another that the chance they have to touch one another, right, that a particle could move and just keep soaring in a particular direction. And it would take as far as the sun to the earth for one particle to even hit another one. That's what we call the mean free path. That's how vacuous the solar wind is. Okay? So basically you have to have a spider web that has electric fields and magnetic fields that are connecting particles that are so far apart that if they didn't have the electric fields and magnetic fields to help them interact with one another, one wouldn't even know that there was another particle nearby until they moved as far as from the sun to the earth. That's how far it would take to get to another particle. Pretty crazy, huh? So keep that in mind when we talk about the solar wind. This is a very vacuous, very much a vacuum, but there is still a lot going on even at that. And really what is the driving force of this stuff are the electric and magnetic fields. Okay? So hopefully that's pretty clear. Let's see if anybody has any questions about that. Texas Flash Code. You're so funny. Elon's here. Yeah, I don't think so. It would be fun if he were, but I have a couple friends who know Elon, so I think he's a little busy to be here. But hopefully some of his engineers are are learning space weather. If not, they will soon. They'll need to. Okay. Been bothered by strong electric shocks. I touch them when they get shocked too. Actually, that's an issue that the astronauts have to deal with all the time. It's also an issue we have to deal with in space, and at the very end, in near Earth space with satellites. And if you stay near the very end of the course, when I go into a small primer about geomagnetic storms, I might touch on that and let you know. So if you want to stick around that long, feel free. Okay, good. I'm so glad you guys, you're understanding collisionless plasmas. Oh my gosh, that's funny. Wow, Chemical spirit, that's funny. Okay. That's cool. You know, write me a letter, tell me about your dream. That'd be awesome. Will this video stay up? Yes, yes. All of my mini courses stay up forever. I was going to take them down. I decided that I'm going to probably leave them up because there's so much dialogue like this that's just kind of fun and playful stuff. So if you want to scan through them to get the technical content, feel free. This one I feel is a little bit more relaxed than the others because I'm still trying to calm down from my mic debacle. So I'll try to get more focused here as time moves on. Let's see, electric and magnetic interactions, are they described as the same? One cannot exist without the other. Yes, Troy, take a look at Maxwell's equations, for example, if you really want to get your mind blown. You may not be able to get through the jargon of it because it's all written in a very funny mathematical language. But magnetic and electric fields are like two sides of the same coin. If you change a magnetic field, if you change a magnetic field in time, for example, you create an electric field. If you change an electric field in time, you get a magnetic field. You can't have one without the other, and especially when they're changing. So where things get a little bit different is that you can have electric fields that emanate from one point. You can't have a magnetic field that emanates from one point. Magnetic fields always have to close somewhere, so they always have to be a closed circuit. Electric fields don't. They can actually be open and just go out forever, but magnetic fields must close. So it's like it's always a closed loop, and that's one of the reasons why a lot of scientists enjoy looking at, not enjoy, but find looking at the magnetic field as the main descriptor of what's going on as opposed to the electric field, because electric fields can get a lot more difficult to measure, more complex, change much faster, whereas magnetic fields we always know close on themselves, and the laws are more intuitive in many ways. So it allows us, and that's why you end up seeing, for example, when I show you the sun, as a matter of fact, as I'm showing right now, I should get out of the way. Actually, let me stand on this side. What you see here are here's a picture of the sun, right, in 211 angstroms. Remember I talked about that before. You can see the coronal holes, right? You can see all the dark spaces, right? But you also see all these lines. These lines are magnetic field lines. So we have a magnetic field model that we use to describe what we call the potential field of the sun. This is a potential magnetic field. It's a very simplistic it's a very simplistic and what we call analytic description of the sun's magnetic field, given what the magnetic field is at the surface of the sun. And we find ways of measuring that. And the reason why we use this field model is because it actually shows us where these closed magnetic field lines are. Do you see how they loop in on each other? Where those field lines close really close to the sun, or where some field lines, if you can see them, actually just go straight out. We call those open magnetic field lines, and where they close is all the way out at the edge of the solar system. They come back to the sun. They go out to the edge and come all the way back, or somewhere along, out in the solar wind they'll close. But they don't close really close to the sun. And you notice, and I'm kind of jumping the gun here, but if you notice, and this is a hint, that these open magnetic field lines, they're the ones where the solar wind, the fast solar wind comes from. Notice that they come out mainly in the coronal hole region. Whereas in the bright regions, that's where you see these ones that close. This is a much easier descriptor of what the sun's behavior is going to be and what is dominating the sun's activity and dynamics. It's much easier to describe it in terms of magnetic field lines than it is electric field. Electric field, you wouldn't see patterns like this because it works in a different principle. So they are related. So we know that if we look at the magnetic fields in a certain way, we can derive what the electric fields are. But the electric fields change so fast. And as a matter of fact, in this particular, and there are times when you can have the electric field go to zero. For example, in this potential source field model, there are no electric currents. There's no currents going through this model. That's actually the definition of this simplified model. This is what the sun would look like at complete rest, with nothing pulling and tugging on it at all. All the electric fields are actually what we call, they're not perpendicular, they're parallel to the field lines. So nothing is tugging on these field lines to change them. And even with it being that simple, which we know is not necessarily true, it tells us a lot about what the sun's configuration is and why we see the dark regions where we see them and why we see the light regions and what they're doing. Okay, so I'm jumping the gun here, but you asked a very, very relevant question, so I thought I'd mention it. Okay, so let me move on here. So the observation of coronal holes, as I've already kind of explained to you, they appear on the disk as these dark regions, and you can see a whole bunch of them in 211 angstroms. That's because they have a lower density and temperature compared to the surrounding corona, especially in that wavelength, okay, of light. As you can see, if we move to different wavelengths of light, like here's 171 angstroms, this yellow sun right here, you don't really see that coronal hole, right, in any of those coronal holes on that. And of course in 304, I told you the red sun, look, can you even see any coronal holes at all? Not really. So, and yeah, that's all the same time. I'm surprised, is that really the same time? I think the 211 angstrom may not be. Pardon me looking. I can't tell by the date, but I would have expected to see some activity here. So I think the 211 or the 171 angstroms, this yellow sun may be the wrong disk, but definitely the 304, the 193, the brown sun here, and this one are all at the same time. But as you can see, even at that, you can see that it's a lot easier to view coronal holes in either the pink sun, 211 angstroms, or the 193, which is the bronze sun. The reason why, again, has to do with what layer are you looking at in the solar atmosphere. The different temperatures indicate a different altitude, and so you can only really see them, these coronal holes that really aren't holes, in certain wavelengths of light. Okay. A lot of people have asked me about why do the coronal holes change. We have what we call polar coronal holes that are on the northern and southern hemispheres. If you ever notice, especially during solar minimum, especially like now, you'll see very dark coronal holes in the north and very dark coronal hole in the south. Okay, but it's not always like that. Remember the one I just showed you had kind of coronal holes everywhere. Well, really, the reason for that is because these things actually move with the solar cycle. What we call the large polar coronal holes exist really mainly through solar minimum, but for about 7 years, on and off, but going kind of through solar minimum. But then as we get to solar maximum, and especially the declining phase of the solar cycle, these holes change dramatically. You will see that the coronal holes actually will begin to migrate down from the north and up from the south, and they'll actually spread. Here's an example of a finger-like coronal hole that is going almost all latitudes. I mean, it's really up and down all the way through the sun. And you can actually see it again in soft X-ray as well. Soft X-ray is also another really great way to image coronal holes. We did a lot of that with Yoko. And here's SXI, which on GOES 14, which I'm not even sure that instrument, because it's been damaged, so I don't even know if that instrument is even something that can view coronal holes very well anymore. But if you wonder why during solar minimum, or really during the declining phase of the solar cycle, why we have more solar storms from coronal holes, from the fast wind from coronal holes, this is why, is because as you get to solar minimum and the sun's magnetic field is extremely ordered, and it's it becomes like a dipole field. You get the coronal holes basically in the north and south. And then as the field becomes more like a lava lamp, for those of you who have actually watched some of my my mini courses and some of my work on the solar cycle, you'll know that as we get to solar maximum, the dipole field disappears, and we have what we call a multipolar sun. The sun gets it becomes basically literally like a lava lamp. There's just poles everywhere, and because the magnetic field gets so confused and disfigured, so to speak, you actually get these coronal holes that then migrate down into the equatorial regions, and you get fingers like what you see here. You get blotches like you saw in this other plot here. If I get out of the way, so you can see coronal holes here just pretty much everywhere. They're not really located only in the north and in the south. And I should probably make a chart that actually shows that specifically. Now, how does that work regarding the coronal streamer belt? the difference with coronal holes and the coronal streamer belt, because a lot of people have asked me this question, is you will always see the coronal streamer belt being a bright region pretty much near the equator, or kind of like a band in and around the equator. Whoops, sorry, I've got family that's, if you can hear all this, they're playing. But let me see, let me stand over here. In some of my other classes, you've seen me talk a little bit about the sun's neutral line, and I'll get into that in just a second. And you know a little bit about the dipole field. So if I'm kind of skipping ahead, if this is your first introduction to what the sun's magnetic field looks like, or what the sun's configuration is, I apologize, because this is definitely building off of courses in the past. Hopefully, most of you know that the sun during solar minimum has a dipole field configuration, meaning that and I'll talk about this in a few more minutes. The field can be very simplified. It looks very much like a fridge magnet. So that's why you get coronal holes in the north and coronal holes in the south. And then in the middle, you get kind of like what we call a magnetic equator. It's not the same thing as a geographic equator. It actually kind of meanders like a snake a little bit across, actually, and I should do it down here, across the middle of the sun. And that is where you see a lot of these bright regions. Do you see how you see all that kind of going like this? This is what we call the coronal streamer belt, okay? And it's held very close to the sun by those closed magnetic field lines. Remember I showed you in the last plot, in the purple plot, with those closed magnetic field lines all around the bright region area? Yeah, those magnetic field lines basically jail all that hot plasma, and it keeps it close to the sun. Whereas the dark areas, these coronal holes, are where all that open field is. And so solar wind is able to just stream out from it. Basically, the solar atmosphere is able to stream out from it almost as if it were free, right? Here with the jailed stuff, the magnetic field lines literally act as jail bars, and it prevents that plasma from leaving the sun. So these are things that you can see very easily when you look at the sun. And once again, from the dark regions, you'd expect to see fast solar wind, and from these regions here, that's where you'd actually expect to see very slow solar wind, because it's not escaping nearly as fast or nearly as easily as it does in coronal holes. And that leads me to this chart, where you can see that the sun does create both fast and slow solar wind. And if you look at this plot here, let me get out of the way on this side. What you're looking at here is solar wind speed. So this bottom chart is a chart of time series. And you're seeing solar wind speed going up on the vertical, okay, and time moving forward along this axis from basically February of 1992 to looks like September of 1994, all the way across on that bottom axis, okay. And so what you're seeing is as a spacecraft was sampling the solar wind, you watched as you started out with slow solar wind near solar minimum. And then the solar wind started getting fast and slow, and bouncing and bouncing and bouncing. So you'd have a stream of fast solar wind, so you'd have a period where the solar wind was extremely fast, right here, for instance. And then that stream would disappear, and you'd get a stream of very slow solar wind. And then almost as soon as that was gone, you'd get another stream of fast solar wind, and you'd get another stream of slow solar wind, and it just kept doing it. But eventually, you got to a point where you're just getting into the fast solar wind. Okay, now this, and I'll talk about this later on. This came from a spacecraft called Ulysses, and Ulysses was actually a spacecraft that went over different latitudes of the sun. So as it passed through the low equatorial regions, it was getting slow solar wind only. This is because it was sampling wind from the coronal streamer belt. But as it started moving to higher latitudes, it kept getting more and more samples of fast solar wind. And basically the sun would rotate past it, and it would get a stream of fast solar wind, and then it would rotate back into a slow solar wind area. And as the sun continued to rotate this way, it kept, you'd get a fast solar wind stream, and then the sun rotate, and the stream would be gone, and now you'd be in a region of slow solar wind. But then the sun continues to rotate, and suddenly you're back into a fast solar wind stream again. And that would happen at higher and higher latitudes until you got near to the poles. So as the sun is, so as Ulysses is beginning to go over the poles of the sun, the North Pole or the South Pole, now you're just sampling solar wind from the pole, and you're just getting that fast solar wind from those coronal, from the polar coronal hole, and that's why you're seeing this. You're seeing high-speed solar wind. So we found out when Ulysses was launched, and it was a landmark mission back in the 90s. This was a landmark mission because we didn't understand really how the solar wind worked, and Ulysses really kind of explained a lot of it for us. That really it really matters what latitude you're at and what part of the solar cycle you're at, and I'll get into that probably in the second course. But I'm just beginning to talk about, I just wanted to give you a little bit of a hint about it, because as I've begun to explain, you realize that the solar wind, it's not just stagnant. It's not just something that blows off the sun in a very simple fashion, right? It's complicated. And as we dive more deeply, and this is one of the things that Solar Probe and Solar Orbiter are helping us understand, we're learning that it's an incredibly complicated process that generates both the slow solar wind and the fast solar wind. In fact, some of the theories that we've learned from Ulysses, they're beginning to be blown away just by the few perihelion, the few close flybys that Solar Probe has had with the sun already. We've had like 4, I think, and we've just been absolutely blown away by both what we see with magnetic field and what we see with the plasma data. That has just thrown out some of the theories that we've always had, that the data from Ulysses so long ago gave us. There's really a very complicated magnetic carpet that happens, and there's these little jets and things that shoot out from the sun all the time, and it's really fascinating, because what we thought came out in big patches on the sun turns out that it's not. It's much more fragmented. So I'm not going to go into all of this kind of stuff, but this is just to remind you that it's a very complicated process on the sun to get what the type of solar wind that we see at Earth and further out in the heliosphere, and we'll continue to go into that. One of the things, and this is a model that I've already mentioned, so I had gotten ahead of myself, but we use this as scientists. We use the potential source field model to be able, in order to be able to get us to understand not just where parts of the sun are unstable, but also where the open and closed field lines are. And I've already talked about them quite a bit. So I know this is kind of an ugly picture, but what I liked about it is that it actually kind of highlighted in different colors what an open and closed field configuration looks like on the sun typically, and how complicated it is, right? We just talked about it being a complicated process, and even when we try to simplify it with this potential field model, taking out all the tugging and the pulling of electric fields and just having it be a field at rest, it's still a mess. I mean, look at it. Can you make heads or tails of that, right? So you ever wonder, why do we not understand the solar dynamo very well, and when the sun is going to launch solar storms and all this kind of stuff, and what it's going to do next? Well, this is why. It's extremely complicated, and we just don't have that many spacecraft out there yet that have been able to really sample it, especially close up, to be able to understand its structure and all that kind of stuff. But at any rate, so with this model, I just want to remind you that you can see both closed, really tightly closed field lines. Those are, whoops, sorry, I've got my hand in the wrong place. Really tightly closed field lines, those are in the red. Slightly less tightly closed field lines, these start becoming streamers. They're in the orange. You can see them start beginning to stretch out. And that happens when these fields want to reconfigure, or there's more pressure, there's more buoyancy, there's all sorts of forces that go on that can cause streamers to start coming out. You can actually see the white light image underneath of the corona. You see the streamer, like for instance with this field configuration in orange here, if I'm pointing in the right place. Let me back up a little bit. Here we go. The field configuration in the orange here, you can see the white light image beneath it showing the streamer that's going out, right? That actually shows some solar wind going out. Now that's slow solar wind, that's not necessarily fast solar wind, but you are seeing how the magnetic field kind of is guiding what the dynamics of the solar atmosphere and what the dynamics of the solar wind is, okay? And then up here in the green, those, whoops, let me go over here. These are the green open field lines in the north. And so we have fast solar wind coming out of here. And down here, you can hopefully see it, blue, the blue, light blue, cyan kind of lines, those are showing open field lines in the south, and you've got fast solar wind coming out in the south, okay? And this configuration, believe it or not, is pretty close to solar minimum. I mean, this is not horribly complicated. The sun can get much more complicated during solar maximum than this, because this is showing nice clean lines up at the open lines in the north, nice clean open lines in the south, and kind of a closed configuration everywhere else. And believe it or not, the magnetic neutral line, meaning the magnetic equator of the sun, is kind of meandering in and around through this region here, okay? And we'll show that a little bit more. So as we take that potential source field model and we kind of overlay it on images, you begin to see a bit more of how it works. And I've already shown this just a little bit, but you can see again, see these bright regions here. Now this is a much more complicated sun, right? This is no longer pretty dark regions in the north and the south. Those coronal holes are gone. What you get is a bunch of coronal holes in the middle of the sun, and your coronal streamer belt's kind of all over the place because this bright, see this bright patch of stuff here with the closed magnetic field lines here, and you get another patch of bright stuff up here. Whoops, let me go down a little bit. Okay, this is more like a sun close to solar maximum, okay, or at least the declining phase, but it's close. It's definitely not solar minimum. And if we try to diagram what the solar wind looks like, if I stand out of the frame, you can kind of see over here, this right here, is showing where some of the streamers are during this period, okay? And here's just above it is an eclipse view of this, a photograph view of an eclipse, and then the sketch right below it of that time period, and that's what it looked like. So you can see that you have open field or open solar wind or open atmosphere, open field lines that are giving you these big open regions here, but you see a big streamer coming out this way from those closed magnetic field, and then you get slow solar wind coming here. You have open wind coming out this way, and you have another streamer coming out on this side. And that's comparing to this observation here. Okay, so these magnetic field models really tell us a lot about what's going on. And if I return, as we learned that we could do this, as I return back to that same picture of, let's see, should I stand over here? I'll stand on this side. To that same idea of using the field model, we can actually then realize that the closed magnetic fields can create, you know, coronal, or we can have coronal holes that are coming up that are at the north. We can diagram them in such a fashion that we can begin to start looking at how the magnetic fields contribute to certain aspects of the solar atmosphere. So we can have little streamers here, if I can point in the right place, little streamers here, and you can see the little arrows showing where the magnetic fields are. You can have small streamers here, you can have big streamers going out in the south, you can have coronal holes in the middle, you know, right around in this area. And I'm not going to go into what the sector boundaries are and all that kind of stuff just yet, but you can start seeing how complicated it can get very, very quickly. Okay? And I don't know if I'm going to talk about the sector boundary quite yet. I had this chart set up for my Millersville class, and I guess I could talk about it. One thing that I wanted to kind of go into, let me see if I can go into something else first before I do this. One thing I don't know if you guys have much, let me do this one first. I wanted to explain something first that I had talked with my Millersville classmates, so I really didn't have these charts ordered the way they should be for you all. One thing I wanted to talk about earlier is about the idea of the slow solar wind. When you have a magnetic field configuration, and if you look at the dashed lines here in this diagram, you can see that's kind of that magnetic field closing in on itself I showed you before. Well, if you have that, what we call these they're oftentimes called helmet streamers from the coronal streamer belt, and they're closed like this. But if you begin to increase the pressure, the internal pressure of the solar wind blowing out, what ends up happening is that these field lines end up being stretched out further and further and further away from the star. So instead of having just these small little loops, they get more elongated, and eventually they stretch out really up and down across all the way out to the edge of the edge of the heliosphere. And these are the regions what we call the slow solar wind. But the thing is that as these regions get stretched out, if you think of the magnetic field pointing outward in this direction and then comes back in because it has to close, it points in this direction. If you stretch that out like a big long, pull it like a big rubber band, and you stretch it out and stretch it out and stretch it out, the field that was pointing this direction gets stretched out this way, and the field that was pointing in this direction gets stretched out this way. So you have field that's pointing in opposite directions, and they become very close to one another, okay? And that is what we're seeing here with this current sheet, with this region here. So as you begin to stretch these streamers out, these helmet streamers out more and more and more, you end up developing a current sheet, okay? See that there? And you'll see very shortly, this current sheet is essentially just an extension of the sun's magnetic neutral line. And it just stretches out into interplanetary space. And it's because you've got the pressure from the star, the solar atmosphere, blowing out at all times. And the stronger that pressure is, you can actually have these streamers form. These helmet streamers form. We've actually seen what we call streamer blowouts. We watch these things erupt. And where there was really not much solar wind coming from, we'll end up getting a new source of solar wind from that region. And this is all from, believe it or not, this is part of what Eugene Parker, back in the 1950s, started postulating with his Parker spiral and the solar wind. And I'll talk about that here in a second. So let me see if I can go to another slide here that I wanted to. Yeah, I can do that, and then I'll come back to that. So let me just show you, if you take that idea of blowing that streamer out and creating a current sheet, then if you start thinking about the entire sun, doing that all the way around the sun, suddenly you begin to get something that's kind of like a sombrero. Because what happens is that if you have a neutral line on the sun, right, and here's a dashed line showing that neutral line, and I told you kind of meanders. This is where all those bright regions are in that coronal streamer belt. That neutral line that's kind of meandering, as you extend that out into space, you have the field, and you can see these field lines. I'll show you this one here, this edge one over here. See, this field line is the one that's coming out of the top of the sun. That's the part of the streamer that kind of got blown out into a long stream. That goes on top of that little sheet, and then you have the return magnetic field coming in from below, and that goes underneath the sheet. Do you see that this field line here? Oops, let me try to point to the right place. Up, 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 up. See that? That's now pointing in, and it goes underneath that sheet, okay? And this process is repeated, and you can see it kind of peeking out again, right? Down, 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 right there. That's that field line, and it's returning back into the sun. That used to be a closed loop that then got blown out, okay? And in between, where that field went out that way and then comes back this way, in between is that sombrero hat, okay? But as that sun rotates, and as you see that neutral line kind of wavering like that, it makes kind of like a brim of a hat, a really floppy hat. And as the sun rotates around, you're going to see that floppy hat kind of spin, rotate, kind of look wobbly and funky. That's what they're trying to show you here with this kind of grayish, I don't know what you call this, flattened donut thing, floppy donut, I don't know. Sombrero without the top part, right? This kind of skirt, in a sense, as you can begin to see what I'm about to call it. As I talk about this and we start looking at this from a slightly different perspective, you'll see that this current sheet becomes what we call the ballerina skirt, and I'll show you that in a sec. but it's really just an extension of that neutral line, because again, you have magnetic field going out this way in one direction, you have magnetic field coming in this way in another direction, and in between has to be a current sheet, because that magnetic field, when you go across it, has to flip. And the only way you can do that is to have electric and magnetic field, or electric fields in between. So remember I told you at any time magnetic fields change, you create an electric field? So if you go from this side to this side, that magnetic field has got to go from pointing this way to pointing this way. And the only way it can do that is to have an electric field in the middle. So it creates a current sheet in the middle. And that's what that sombrero is. Okay, hopefully that makes sense. And you'll see in just a minute that it's an extension of the solar wind. So when I go back to this picture and I talk about, we'll just talk about this diagram here, and I talk about this helmet streamer blowout, you can see now when I describe this thing going out, okay, and you see the positive here, whoops, back up here, positive sector and negative sector, okay, what I'm talking about is positive being out to the solar wind, the magnetic field pointing out into the solar wind, and in the negative sector it's pointing back toward the sun. And in between that is that dashed line, that's a current sheet. So every single one of these streamers that you see, okay, believe it or not, every one of these little streamers that you see, even on this side over here, as they blow out further into the sun, out into the solar wind, they actually have little current sheets of their own. But there's always one that's the big one, and we call that the sector, we call that the heliospheric current sheet, because it comes from the magnetic neutral line on the sun. And that's what I'll get to now. Okay? So is that clear? Anybody have any questions about that? I know it was a little, I kind of shifted charts around a little bit. I probably should have rearranged these charts for this class. But hopefully it's somewhat clear. It'll get more clear as I continue talking about the neutral line on the sun. But any questions on that? Let's see, does the current have charge particles? Wait, does the current have charged particles? Yes. Or is it just a displacement current? All electric fields and electric currents have to have particles that are carrying that current. So yes, there is the neat thing about the solar wind, of course, is that you have positive and negative charges all the time in the solar wind, and usually it's what we call quasi neutral, for lack of a better phrase. It's a quasi-neutral plasma, meaning that you have as much positive charge as negative charge in general, unless you have something like this happening, and then you have, in this case, either more electrons or more ions, depending upon what it is you're doing. Usually more electrons, because electrons can move more quickly than ions can. So you end up having a disproportionate charge. That it doesn't take much, obviously, but because the magnetic fields are weak and there aren't many charges, there aren't many particles to begin with, so it doesn't take much difference to change, to be able to create these current sheets. But yes, there are particles. There's always particles in the solar wind, so you can always create electric fields and you can always modify magnetic fields with them. Hopefully that answers that question. Great info. Okay, good. It's making pathways, yes. And that's one of the reasons why we follow the magnetic field of the sun, because the electric fields change so much. When we get electric field instruments, boy, it's in the spacecraft, with spacecraft instruments, boy, they're hard to read, because we get burst modes, we get waves and things that just go crazy with the electric fields, and they're so incredibly difficult to read, especially when you want to see the overall behavior of something. Because if you have plasma waves and growth and all this other kind of stuff, things that are trying to, I don't want to say isotropize, things that are trying to smooth out temperatures of particles. Like some particles over here are hot and others are cooler. There's always this desire to, cool down the hot stuff and heat the cold stuff. It's just like when you have a hot cup of coffee, right? Why does it always cool down to room temperature? Or why does a hot coffee heat the cup? Why can't the cup stay cold? That kind of thing. It's the same kind of idea. It's entropy, basically, is what it is. And so we have those processes in the solar wind. And the reason why it's so difficult to look at electric fields so many times is because how that entropy occurs in the solar wind is through electric fields and waves. And so there's all this other hash and all this other stuff just going on all the time with electric fields in the electric field measurements that the magnetic field measurements, no, they see it, but a lot of times it's easier to just, it isn't as hard to read through. So electric fields are changing much more, I don't want to say more rapidly than magnetic fields, but they're changing more dynamically. And so that's why a lot of us choose to look at magnetic fields as opposed to electric fields. But we always have to consider them both. So yes, that's kind of how the whole thing works. Hopefully that answers that question. You measure the fields use of a magnetometer. Yes. What other instruments are used? For magnetic fields, we use magnetometers. That's the main way we use them. You can derive magnetic fields from electric field measurements, and indeed we oftentimes use magnetometers to infer either the electric field or what the plasma, what the particles are doing. You can do that if you're savvy. Of course, you have to make certain assumptions, but because they're all related, you can kind of get, if you make certain assumptions, you can get some information about stuff that you're not even measuring simply because one affects the other. But yes, the main way we measure magnetic fields is with a magnetometer, and we have to get that magnetometer on a boom that sticks way out. So anytime you see a spacecraft and you see a really long arm and it doesn't look like an antenna, then you know that that's the magnetometer boom, and on the end of that is where the magnetometer sits, because you have to get the magnetometer really far away from the spacecraft in order to be able to sample the pristine solar wind. Otherwise, you get a lot of noise from the spacecraft, and you can actually get yourself stuck in a shielded region inside the spacecraft. That then you won't be able to have a clue what you're actually measuring. So, oh, thank you. I appreciate that. Okay, can anybody define a field? Wow, it depends upon what I have a spider web if you want it to be jargonless. If you want it a physics description, that's going to be beyond the scope of this class. It is very easy to define a field, but the question is, will you understand the definition? Because fields are I don't want to say by definition, but sadly, electromagnetic fields are some of the hardest stuff to understand in physics because you can't see them. You can see their effects, and you can get them by proxy, but you have a real hard time actually seeing them unless you take, iron filings and put them near a magnet and watch how the magnet changes the way they the forms that they make, and then you can kind of see the magnetic field lines of that field emerge just simply by the behavior of that. As a matter of fact, if I go back to a picture of a coronal mass ejection, a big solar storm being launched from the sun, and you see it in a big loop, what you're seeing is a field. You're seeing the effect that those particles have, just like a magnet, just like the iron filings with a magnet get shaped, into particular lines and forms based on a field that you can't see. So this is the same with these big solar storms. When they're launched and you see them in big loops or big tubes, those shapes are exactly the same thing. The magnetic field is shaping that plasma in a certain configuration because it jails it. And so it's hard to define a field without using mathematics and jargon because you can't see it directly. Okay, but that's why we ended up calling things like a force field. It really is a force field. Electric and magnetic force fields, if you want to call them that. We just dropped force, but all of these fields do apply some kind of force, an invisible force, on things around them. Gravity is a force field as well, right? So gravity has its own field, and in a jargonless description, it's really pretty much something that applies a force to you, or applies a force to let's say some particles or some object of interest. It applies a force to it, and you can't see where that force comes from. So gravity is probably the easiest and most intuitive force field that you deal with on a daily basis. And of course, as you go up in altitude, that force field diminishes, right? It actually is less, you have less of that force on you because you're getting further away from the planet. So the pull is actually less. You actually weigh less higher and higher in altitude than you do here. It's almost imperceptible it's imperceptible to us, but it is measurable. But that's probably the best jargonless definition of a field that I can give you. It really is a force field, and I hope that helps. Outside of that, we'd have to get into math and I'd have to break out pieces of paper and start drawing things for you, which is, again, beyond the scope of this. So hopefully that helps. I guess the word field is the issue. Yeah, I mean, field isn't like a grassy field or a baseball field. In this case, it's an invisible area or region that then, when you're in it, you actually are, your behavior is dictated by it. It actually applies a force to you, and that force may not be the same depending upon where you are inside the field. Okay, so it could be a completely, unusual looking field that is very different from one end. The force that's applied to you is very different from one end of the field to another. That's the best I can do for you here. So, all right, I don't want to get too far off the subject. Does entropy have any effect on the sun's field? Of course it does. Entropy is happening all the time. It's trying to make everything homogeneous, right? And it causes both things to grow and things to decay. And the sun is always trying to get to a relaxed state, so it's always shedding things. That's part of the reason why there are solar eruptions to begin with. It's always trying to shed all this extra energy and reconfigure itself to a lower energy state. And that's entropy. That's entropy at work. And so, yeah, it's affecting everything that the sun does. But entropy affects the state of my daughter's room. It affects everything, right? It affects the ice melting in my glass of water over there, which I need to take a drink of. So yeah, I don't want to fall down into just a discussion of basic thermodynamics and physics. I do need to get back to this, but hopefully, I know some of these concepts are a bit intense, but it's really, you could even just Google entropy and Google some of these things and get maybe a better understanding offline about what some of these more basic physics concepts are. I'm just really trying to get you to understand how they apply to to the space weather and why, for instance, the magnetic field is such a big indicator of what we do and why we use the magnetic field. Because I know there's a lot of electric cosmology people out there who say, no, everything's electric, just look at the electric universe and blah, 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 blah. Okay, fine, you do that, and you have fun interpreting that, because I'm going to stick with magnetic fields because to me they're easier, and they're both related, neither of them lie. So, I'll continue looking at magnetic fields to try to understand the sun, and you guys can try to figure out the sun just using electric fields alone. God willing, you'll be able to do that, but I don't have any faith that people can look at electric fields on the sun alone or in the solar wind and think that they can understand the fundamental nature of the solar wind and the sun itself. It's too complicated, especially with the measurements we have. We're not very good at observing yet. So, okay, so let's get back on this. I have a fluxgate magnetometer for finding anomalies underground. Yes, fluxgate magnetometers, they're also cheap and they're very reliable. So if you can calibrate them, they're fantastic. And we use fluxgate magnetometers all the time on spacecraft. That's what we put out on the booms. Typically, it's the magnetometer of choice. So it's great that you have that, because that's exactly the type of magnetometer we use on our spacecraft. Okay. So let me get back to the coronal field structure. Remember, we're talking about, once again, magnetic field on the sun. Let me stand over here. What we're looking at here, these are ground-based observations from Mount Wilson Solar Observatory, and I believe what we're looking at here is this is kind of a smeared. I think this one is a model of the magnetic field. Oh no, it's extrapolating the photospheric field. At 5 solar radii. Okay. If I look at the image in the middle, this is the magnetogram that is obtained by looking at spectral lines in basically the HMI, an HMI type instrument. We're looking at magnetic field, we're looking at Zeeman splitting, and I won't even go into it too much. And we oftentimes use Doppler shifting to be able to understand how the magnetic field if it's coming in or coming out of the sun or coming into the sun. And that's why you see it done in grayscale, is because it's actually looking only at field coming in or going out. The black is field going into the sun, and white is coming out. So you can actually see in these in this what we call a Carrington plot, you can actually see some active regions. That's the black and white kind of little spots that come together here, 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 here. You see them. Now, before I forget to tell you, this Carrington diagram is basically taking the sun and unwrapping it across its entire disk, like taking the entire globe of the sun and unwrapping it. And longitude goes across the horizontal, so from 0 to 360 degrees. So that's one whole revolution, one whole rotation of the sun. And then what you're looking at here is latitude. The equator, the geographic equator of the sun, is right in the middle at 0, and then you go up to 90 degrees in the north and down to 90 degrees in the south. And when we look at the photospheric field, this is the field that's on basically the surface of the sun or close to the surface of the sun, we are able to kind of start seeing where the magnetic field changes from either going in or going out. Okay, and like I said before, the white is going out toward, so in other words, toward the camera, toward the imager, and black is going in. Okay, so you can see in the southern hemisphere, in this particular Carrington diagram, you have the main part of the sun's field going inward in the south, and it's coming out in the north. So that means you have a sun where the field is coming out this way and going down and coming back in the southern pole. And that's the dipole part of the field of the sun. So that's the overall field. But in the middle, it has to change. We have to have a neutral line of sorts, an equator of sorts. And that's what this yellow line is showing. Notice that the yellow line, which is the magnetic equator of the sun, is not the same as the geographic equator, which is that dashed red line. Okay? So again, the field in the northern hemisphere, what we call the radial field, that's the field that's pointing outward or pointing inward. It's coming out in the northern hemisphere, that's the white color. In the southern hemisphere, that's the black color. Okay? And then of course the magnetogram shows all sorts of fields of gray. This is because it's much smaller scale. Okay, and it's slightly different location. It's not 5 solar radii out. It's it's on the surface of the sun. But here's the interesting thing. This is a plot of what the solar wind velocity that would be predicted from this magnetic field structure. Okay? Notice the blue is the slow solar wind. Okay? The green and red and yellow, that's the fast solar wind. Notice how the slow solar wind all comes near the equator, right? It's all near, and it follows that magnetic field, that magnetic neutral line. Okay? The reason for this is, again, that magnetic neutral line kind of talks about where those streamers are, right? It's right where the field kind of stops, it goes out, it stops being radial. The field comes out radially toward you, it stops as it begins to flip back over, and then it goes in the southern hemisphere. Where it stops being radial, in other words, where it doesn't point out or in, it's pointing in this case down, that's where the magnetic neutral line is on the sun in terms of the radial field, because everything above it is pointing slightly outward and everything below it is pointing slightly inward. The easiest way to remember that is when we talked about those streamers, right? We had those streamers, and as you stretch out those streamers, you get field that points out radially and field that points in radially right below it. And you get that sheet in between, right? Well, if you map that sheet all the way back to the sun, you're mapping it back to that yellow line. You're mapping it right back to that magnetic neutral line on the sun. And lo and behold, that is where you get all the slow solar wind. Now, where this becomes interesting is that, remember, the sun rotates, right? So remember that floppy hat. If that magnetic neutral line that you see, that yellow here, or obviously the blue down here, if that magnetic neutral line and that slow solar wind is kind of flopping above and below the geographic equator, then as that sun rotates, that location is kind of flopping above and below what we call the equatorial plane, meaning the midpoint. And the Earth sits essentially in that equatorial plane. So if the neutral line is above that plane, then maybe the Earth won't see slow solar wind because the slow solar wind is actually going above the Earth. Instead, maybe it's going to get a region of faster solar wind. And what happens when that neutral line flops as the sun continues to rotate and that neutral line dips down below the equatorial plane? Again, Earth is sitting above, and now you've got the neutral line, where I'm the sun, going below that equatorial, what we call the ecliptic plane, right? So it goes below Earth. And again, you no longer sitting in slow solar wind. So what ends up happening is that as the sun rotates, and that floppy hat that we talked about, this floppy hat behind me, as the sun rotates and that floppy hat kind of flops up and down as I rotate, right? My hat is kind of like tilted this way, right? And it does one of these as you rotate. I know I look like a fool. That if the Earth is sitting here, it's going to hit that hat, it's going to get part of that hat hitting it, and then it's going to miss that hat, and then part of the rim of that hat's going to hit again, and it's going to pass above and below. But if that hat, if that current sheet kind of dictates where the slow solar wind is, well then suddenly what was once just a straight stream of solar wind all the time no longer becomes a straight stream of solar wind, a slow solar wind all the time. You get spurts. You get a burst of slow solar wind, and then you move out of the slow solar wind and you get a burst of fast solar wind. And then you get a burst of slow solar wind again. Another way to look at it is if I'm the Earth, and I'm down here in this bottom panel, right? Okay, and I'm sitting essentially, let me try to get my hand in the right place. I'm sitting here essentially at the equator. Okay, essentially here. Earth goes kind of above and below by about 3 degrees. It's really not much different. It stays pretty close to the center. If I'm here, okay, I'm going to get close to the slow solar wind at the beginning of this, but as the sun rotates past me, I'll end up dripping out of the slow solar wind and getting into the green. I'm no longer in the blue, I'm in the green. And then as the sun continues to rotate, I'll end up going back into the blue. That's the slow solar wind. And then as the sun continues to rotate, I'll go back into the green, maybe in this case just a little bit here. And then I'll pass through the blue again, just a little bit, and I'll be back into the green on this side, maybe even to higher solar wind, maybe where the red, oops, pardon me, here, maybe even where into the red solar wind, which is even faster than that. So as you can imagine, depending upon how undulating this neutral line is, which is representative of that coronal streamer belt, depending upon how crazy it is, that will dictate how much fast and slow solar wind streams I'll see. Okay? Now imagine something like this. Here is the one we just saw. This is the current sheet and flow structure. Whoops, sorry, put my hand in the right place. This is the one we just saw. This is the current sheet and flow structure of the solar wind near solar minimum. Okay? Everything is reasonably smooth. You know, the neutral line isn't undulating too much, but it does a little, right? And that's the kind of configuration you get. But what happens at solar maximum? Look at this mess. Holy merd, see a difference? Now, first of all, the savvy people in the audience will notice that even in the top panel here, you see white up top and black down south, but in this panel you see the opposite. So you'll know that this is a different solar cycle, right? Or you've seen that at least the polar field switched, because in this case, north has radial field going in, and south below the equator has radial field coming out, because the locations of black and white have switched. But the other thing that's also very telling is look at that neutral line now. Wahoo! Look at that roller coaster. Do you see that? And look at all these active regions. Holy merd. Do you see all those? I mean, it's just a zoo, right? So this is what happens when the dipole field goes away. When the dipole, the nice smooth field of the solar wind, and that we get during solar minimum, that smooth field configuration begins to disappear. And it's not completely gone here, not yet. I'll show you an example where it's totally gone, but it's getting pretty dicey. So suddenly you can see with these excursions of the neutral line coming down to really, high latitudes. In this case, this one here comes up to 45, almost 50 degrees. If I can point in the right place, this black right here, see that? That neutral line comes down to almost 50 degrees at southern latitude. Well, what happens here is that when you get the neutral line diverging that far, then that means the streamer belt is diverging that far. And that means in these other regions, you can have coronal holes. So this is what I was talking about during solar maximum and during the declining phase, how you can get coronal holes that are no longer sitting near the poles of the sun anymore. They're now coming down into lower and lower latitudes, even down to the equator. Okay? And look at the solar wind that we've got. Look at this configuration of the solar wind. Now the slow solar wind, granted the band is a lot bigger, but look at where the fast solar wind can come. Right? We're seeing the fast solar wind passing through the equator, the geographic equator, clear down into the southern hemisphere. Why? Because our magnetic neutral line has diverged so much. So imagine what that floppy hat must look like now. Right? You thought it was a floppy sombrero before. Holy merd, now it's like, my goodness. I mean, it looks kind of like maybe a ballerina skirt, right? Like tutu. Right. So, kind of putting this together a little bit, let me give you a little idea about how the solar cycle works. For those of you who have not seen any solar cycle, this should be able to clear your mind just a little bit, or help you assess it just a little bit. So what you're looking at behind me are what we call these same kind of synoptic charts, but in this case, they're written, basically drawn by hand. Okay, these are, once again, I think from Mount Wilson. Yeah, it's Huxama, so of course they are. So these are synoptic charts from Mount Wilson, and these are Carrington numbers on the side. So you see 1742. That's not the year 1742. That's Carrington rotation 1742. The year is actually on the opposite side. This is 1983? Yeah. So this one says 1983. These are the years. And then, sadly, when you get to the other column, they switch. The years are now on this side. Sorry for the confusion, but that's just the way he did it at that time. And then the Carrington number is on the far edge. So if we follow this kind of in time, you go from 1983, which was near solar minimum, and you can tell because look how gentle that neutral line is, right? You see in the northern hemisphere it's all black, right? And in the southern hemisphere it's all white. Right, and the lines are showing contours. So the strengths of the magnetic field in that sense. You don't really see any contours with the black side, but you see them with the white. And of course, where that switches from black to white, that is right where the magnetic field switches. So that first one is, and it should look a little bit thicker, but it probably doesn't. That is the magnetic neutral line. So you can see it kind of undulates all the way across the sun. And over time, it changes, right? 1983, 1984, 1985. You start seeing, by 1986, I think, as a matter of fact, I think was it December of 1986 or the latter part of 1986, I believe, was really solar minimum. And look how flat, if I'm not blocking it. Am I blocking it? Well, yeah, kind of. That is solar minimum. I mean, that is about as solar minimum as you can get. That neutral line is almost exactly the same as the geographic neutral line, almost dead flat across. That is a very well-ordered sun. As a matter of fact, if I stand here, you see the arrow. This is what basically the sun's magnetic configuration looks like at that time, is this figure B. You've got a very nice, very well-ordered polar coronal holes you see in the north and the south, essentially two big streamers, and a very what we call dipolar configuration. Remember, a dipole magnet looks, I probably should get a picture of a dipole magnet, where you've got the field coming out of a bar that comes out like this. And you just have beautiful field just kind of wrapping around in two big elephant ears, which is what you see here. The only difference, of course, with the sun is that you've got that pressure stretching those ears out at the edges and going like that to the edges of the ears. Whoops, if I can point in the right place. You point here, here's the edge of the ear. Okay, right here, that's some slow solar wind coming in there at the edge of that ear, and then of course on the other side, right back here, yeah, that's the streamer. Okay, that's where it's being pulled out. But overall, the configuration is very, very smooth. It's a dipole configuration, and the synoptic chart, the magnetic neutral line, looks a lot like this. Okay, but then what happens, right? We get out of solar minimum, the sun begins to get a bit rattier and rattier and rattier, and by the time we get down here, what's happened is that the sun is actually tilting. The dipole field configuration is beginning to change, and it really manifests initially as a tilt of the dipole. Okay, so you're seeing that, it's getting more what we call multipolar, but the dipole field hasn't disappeared yet. But it really starts making the dipole field tilt and kind of sway and bend over, and that's how we know that this happens both in the rising phase of the solar cycle and the declining phase of the solar cycle. But then as we continue to move forward, so you go from this configuration, and it's kind of looks like a bit of a jump, and it shouldn't have been. But here is, back in 1988, this lower part down here, where you get a really big dipole tilt. And then everything just kind of breaks. Suddenly you get the magnetic neutral line being excursion so far that it really begins to create magnetic islands. Anybody who's ever heard me talk about the sun being a lava lamp as we get toward solar minimum, this is why. Look at this mess. 1989, 1990, 1991. Can you even recognize? 1990 and 91 is solar maximum. Can you even recognize? Well, I think it was actually 89 and 90, but close enough. All of these like 4 panels up here. Can you even recognize a neutral line? Do you even see a magnetic neutral line? Where's the coronal streamer belt? Where would it be? I mean, you're looking for a neutral line, and that's going to be the coronal streamer belt. Good God, where'd it go? It is. It's just a lava lamp, isn't it? That's what happens when the dipole field of the sun disappears. And when you get there, this is what the sun looks like. Can anybody say coronavirus? So maybe this is why they called it coronavirus, right? Because it looks like the sun at solar maximum. It is the corona. It's very much the corona. Weird how life has the universe has these little inside jokes, right? We call it a coronavirus, and wow, lo and behold, it looks like the sun when it's angry. It looks like the corona when it's angry. So this is a multipolar sun. All remnants of the dipole field of the sun are gone. The coronal holes are now small and everywhere, right? Which is what I showed you early on. I showed you a couple examples of the sun with coronal holes that were kind of patchy and small, not ordered well at all. It doesn't even look anything like this, right? This was all beautiful and nice. And now we're here. Welcome to the lava lamp of the sun, and the sun is just spitting stuff off left and right. All sorts of solar storms, all sorts of solar flares, all sorts of stuff, because it is a mess. It's literally a hot mess. I didn't mean to make that joke, but it really is that. So then, as the dipole field flips, okay, because now the dipole field's gone to 0, and now it's flipping again. Now we get the configuration changing and reforming. Notice as we get down to these lower panels here, where's the black and where's the white? They flipped, didn't they? Black used to be at the top. Look at these panels over here. Black was top, white was bottom. Black was north, white was south. Now look, once we've gone through solar maximum, black is now south, white is now north. That's because the dipole field, it reversed. It went through 0. We had a multipolar sun, a big coronavirus sun, and now the dipole field is building again, but it's building the opposite direction. So now black is on the bottom, white is on the top, and, oh my gosh, we have a neutral line again. But it's really crazy neutral line. It's back to being this crazy configuration over here, right? This really tilted dipole, okay? So we have a real tilted dipole again, but now it's tilted the other way. And as we start moving away from solar maximum in through the declining phase of the solar cycle, down into solar minimum, look, the neutral line is getting smoother and smoother and smoother again, right? Until eventually it'll look very much like this. It's just the difference will be that black will be on the bottom and white will be on the top as opposed to the other way around, okay? And that's what this is working toward, okay? So you can imagine if that heliospheric current sheet, okay, that ballerina skirt, is very much an extension of this neutral line. And this neutral line is changing depending upon what the sun is doing, primarily what the sun's magnetic field is doing. And remember, the sun's magnetic field jails everything. It's that collisionless plasma that jails, the magnetic field confines that collisionless plasma, and it jails all those charged particles that see the electric and magnetic fields. So those particles in the solar wind, as they're being blown out, they must obey. I see and I obey, Mr. Sun. I will do what you command. Whatever your magnetic field commands me to do, I shall do. So when the sun says we have a very floppy, crazy-looking ballerina skirt style current sheet that goes out into the solar wind, well, that solar wind is going to have a very complex behavior as well. You're going to have lots of fast and slow solar wind streams, and we'll talk about that in a minute. And then during solar minimum, when everything is nice and smooth, you're not going to get many streams, right? Things are going to calm down. It's going to be pretty quiet and pretty much slow solar wind, which if anybody's been following the solar wind lately, everybody's very tired of 300 kilometer a second solar wind. We're like, where's the 700 kilometer, 800 kilometer, 900 kilometer a second solar wind fast streams that we saw just 2 or 3 years ago? Well, they're gone because our magnetic neutral line looks like this. It no longer looks like this, okay? Or even this down here. Or we had a nice dipole tilt to the sun, and we had those solar wind, those fast solar wind dips, you know, that big bursts of fast solar wind with the coronal holes dipping down into low latitudes. So let me, before I go into the Parker field, let me see if I have one. Do I want to show that yet, or do I want to go in the Parker solar wind? I'll give you a hint. This is how crazy the ballerina skirt can get. Okay, and I'll talk a little bit more why it looks like a pinwheel in just a moment. That has to do with the Parker spiral. But just to give you an idea of what that floppy hat can look like as the sun continues to spin out and rotate, this is what the floppy hat looks like. And you can imagine everywhere, if you are the Earth, and here's, they tried to show a planet over here. This, I guess, is supposed to be Earth. It's a little flattened. But if you are the Earth and this sheet passes over you, when the sheet passes over you, you're pretty much in slow solar wind. But when the sheet doesn't pass over you, you're in fast solar wind, or faster. Probably the further away from the sheet you are, the faster the solar wind gets. So you can imagine as these waves expand outward, you can imagine you're going to see streams of fast and slow solar wind. This is an example of when that neutral line on the sun is very tilted, is very kind of undulating. Because look at this floppy hat of ours. Look at our ballerina skirt. Okay? So hopefully, so I'm going to pause there, and then I'm going to get into the slow solar wind. I mean the Parker spiral. But I want to take a break to catch questions, to see if I've managed to, despite the fact that my charts were kind of ordered in a weird fashion, I've managed to kind of backtrack enough to make sense of things for you. So questions, clarifications, how can I help? Question, will you think solar weather will be a part of what we know now as weather? Yes, that's what I'm trying to work on. Tamitha, I've got to say, I don't think I could ever learn anything you know and how to apply it. You don't have to. That's not the point. I'm honestly changing or training terrestrial meteorologists in the art of space weather without the jargon. So they can get on broadcast news, on the 6 o'clock news at night when there's a solar storm, and say reliably that, okay, here's a solar storm coming, this is what you have to watch out for, just like they do with, with normal weather. Right? If you had to learn everything a meteorologist knows about a hurricane or terrestrial weather, your mind would be, you'd be mush, right? You don't want to have to know that. You've got other things to do. Let the meteorologist do that part for you and tell you what you need to know. Sadly, though, meteorologists right now, when they cover space weather, they get it so messed up and it's just so wrong most of the time that most of the time people get very angry. They think they're going to go out and see aurora, and the aurora happened yesterday. We can't have that anymore. We have to have people safe. We have to have people have fun with space weather, but now we're beginning to move out and become a spacefaring race. So we have to have people go up, you know, in like Aurora tourism balloons and Virgin Galactic and all these other things, and have them be safe and know when the space weather is okay and when it's not so okay. So it's really going to be just like weather, but you don't have to know everything that I'm teaching in these courses. This is mainly for people who want to know that stuff, or who have a vested interest because they're first responders and they need to worry about things like radio communications and stuff like that, that really get affected by space weather phenomena. So hopefully that answers that. Is that why it's 100 Fahrenheit in Antarctica and 16 in Argentina? No, that I'm talking about something that's completely different. How the sun affects Earth climate is unfortunately not my expertise. I can talk about it offline to some degree and talk about the things that I do know, but I think that these are fields that have yet to be melded together. We don't have enough space and space weather physicists and terrestrial meteorologists that have gotten together and really coupled the fields together yet, because there's just we've approached it in a, I don't want to say a very cavular fashion, but we've only just begun to cross-pollinate, and there's just a lot more to learn. Because there's so many more types of inputs to Earth climate than just the total solar irradiance, for example, that the sun gives off, and we don't understand all of it yet. Okay, why did the solar wind just drop off the chart yesterday? Oh gosh, I know, it's crazy, because we are at solar minimum. I mean, we're beginning to climb out of it, but if you look at if you go to Mount Wilson, for example, and look at the synoptic charts for today, there's just a flat line. This is as quiet as the sun gets. Plus, so we are in the slowest of the slow solar wind. Plus, we're in a low activity cycle, which means the really slow solar wind has a very weak magnetic field, about 2 nanotesla, which is about half of what we normally would have, and just for the slow solar wind. And the solar wind itself is even slower than what we used to consider average, which is about 400 kilometers a second. Right now, I think it's sitting at 300, maybe 295. I've seen it drop as low as about 250, 230 kilometers a second, and it just drives me crazy, because it's just snore. You know, the sun is just hibernating, and it's very, very frustrating. I can't wait for the sun to wake up. But that northern hemisphere is still lagging. It doesn't want to move. The southern hemisphere is ready to go to the new cycle, but we have to wait for that northern hemisphere to catch up, and it just hasn't caught up yet. Okay, yes, we need integrative studies then, yes, and that's a field we must create, so that's what all this is all about. We're literally trying to create that field right now, and it's slow going, but we have to train. I've tried to train space weather physicists into the idea of bringing their stuff to meteorology and do more stuff with you know, operational space weather. The problem is, so many people in the space weather field that are academics, they don't want to do operations, because to them operations is engineering, and so they want to aspire to get Nobel Prizes. They want to aspire to look further and deeper and find the great mysteries and the mechanisms behind stuff. They don't care so much about how it, well, they care, but they don't focus their research on how it affects life and society the way terrestrial meteorologists do. A lot of terrestrial meteorologists, it's all about what's happening now. With space weather, it's not so much that, because they're still trying to understand the fundamental mechanisms of why things happen. So this is kind of like an afterthought. And because of that, a lot of people in my field don't look to meteorology as a I don't want to say anything of value, they do, but they just look at it as something that they'll get to eventually. It's just not as high a priority. Now, there are a few who differ. A lot of people at NCAR and UCAR, for example, Scott McIntosh's team, those guys interface with meteorologists all the time. Dolores Knipp is another. There are people who have both meteorology, terrestrial meteorology degrees and space physics degrees, and those people are growing in numbers, and I'm so grateful for them. Obviously, NOAA, SWPC, they're beginning to work that direction as well. The American Meteorological Society, we've got some space weather stuff in there now, and the field is beginning to come together, but it's just very slow. And I am really trying to accelerate that connection, as well as create this field of broadcast space weather. And I think by doing that, it demystifies, for the terrestrial meteorologists, doing that demystifies space weather for them, so that they feel that they can grasp it and they feel that they can understand it. And, hey, this isn't so hard. I don't, you know, I can do this. I'm not. I shouldn't be so scared of space weather, and so that's how I'm trying to facilitate it. And I think it's working. I'm getting a lot of people that are very interested now in space weather who thought they could never understand it before, including a lot of people from our community here. And I'm so very grateful to so many of you, because you guys have helped spread the word, and have brought a huge amount of awareness to the public of what space weather is and what it isn't. And I think we're going to see a monster paradigm shift in understanding as the sun ramps up and a lot more eyes turn back toward us. Because remember, for the past 3+ years, well, 2+ years, the sun has been basically asleep. So we've gotten very little attention. And as soon as the sun wakes up and starts firing M and X class flares again, which will probably be easily within the next year, maybe less than that, we're going to see a radical shift in all of the journal articles and all of the news reports and things like that on maybe even mainstream media about this stuff. And I just think it's a wonderful time to be in this field and to be part of this community, because we are literally on the precipice of going mainstream, and I think it's coming very, very soon. So, okay, it flips in cycles, right? Yes, it flips in cycles. Thank you for Susie for helping answer a question that was obviously in the chat. Everybody can always catch the rerun of this, so please go back if you missed stuff, and take your time, because I know these things can be like drinking from a fire hose. I always give a lot of information, so I apologize for that. Okay, it's always an afterthought. The link between space weather and terrestrial weather is never looked at properly. The sun controls our climate, and so do the planets in our solar system. Yeah, there's all sorts of tidal forces and things that we just are beginning to try to understand. The problem with that is that we understand tidal forces very well, but we haven't had the instrumentation to separate out all the other effects from tidal forces. So tidal forces kind of play a role underneath the surface. I always use the analogy of like having a bathtub, because I have a daughter, right? So I always use the analogy of having a bathtub full of toys. If all the toys are submerged under the murky, soapy water, you can't see the toys. You know they're there, but you just can't see them. Only when you drain the bathtub do those toys begin to emerge. And by understanding the fundamental processes and dynamics of our star and the climate and everything else, understanding those primary processes well enough that we can subtract them off, in other words, drain that bathwater, only then will we see the lower order effects, meaning the toys in the bottom of the bathtub. But we can't begin to do anything but speculate on what those toys are unless we can reveal them from under the water. In order to reveal them from under the water, we have to drain that bathtub, and that means subtract off that water, right? Subtract off those effects that are drowning everything underneath. Does that make sense? That's why mainstream science hasn't gone in depth, and you haven't seen a big rush of people trying to attack those problems. It's not because they don't believe those problems exist. It's that we just don't have a strong enough understanding of what the main forces at play are to be able to subtract them off to see, hey, is this tidal effect causing any issue or not, or changing things dramatically or not? There's been a lot of calculations by scientists that are very contradictory. Some say, yes, it is strong enough to cause a change, and others say, no, it's not. It's much less. It's an order of magnitude smaller. So as long as we continue to have that, that unclear and lack of consensus in the mainstream science world, and there's arguments pro and con, you're still going to see that. You're going to see people kind of say, well, okay, that problem's not something we can solve right now. Let's go solve the easier problems, the lower hanging fruit, and then we'll get back to that later. We'll leave that for the fringe scientists right now until mainstream science is ready. So that's why you oftentimes see mainstream science leave certain things alone. It's not because they don't believe those effects exist. It's just that we can't prove them one way or another how much of an effect they have, because we don't understand the fundamental processes that are much more dominating. So we will get there, but it takes a while. Yeah, and earthquakes, that's an example of, I would think tidal forces play a bigger role in earthquakes than the sun's force. But, that's not something we're ready to tackle yet, not at all, because we don't even understand the underlying Earth, the forcing from just tectonic plates and geophysical point of view. If we could predict earthquakes and understand those more primary, more dominant forces better, then it'd be easier to try to see what are the secondary and tertiary effects of things like tidal forces and space weather on perhaps the seismic activity of our planet. It's just too hard to tell without understanding the fundamentals first. So that's why you don't see geophysicists go after that question, not in mainstream science anyway. Okay, right, wild spirit, yes, that's exactly right. Oh my gosh, yeah, that's a whole other thing. Carlu about Bambi, about about health issues. You know, there are health issues, there's no doubt, and there are more medical researchers who are turning to that all the time. I will end up doing a separate course, probably not a course so much, but I will at some point dedicate an entire Q&A, mini course, so to speak, to the topic of medical research. And the reason for that was not so much to say this with any definitive statement, but rather to say, hey, this study is out there, this study is out there, take a look at this. If you have these issues, take a look at this. This may help you, may not, I don't know. But to let people know that there is medical stuff out there. There are medical research being done with respect to things like geomagnetic storms and magnetic sensitivities and all sorts of stuff like that. So just be aware, and once again, I will talk about that more in its own course at some later point. That is something that some of my Patreon community has specifically requested me to do, so I will do that. As a matter of fact, I've got one of my VIP members, Lourdes Moreto. She is helping me create a database of medical articles and peer-reviewed stuff that is credible and robust, and it shows it, and we can create that database and make it available to people who suffer, who believe they suffer issues related to space weather and just the geomagnetic effects of our planet. If at all that can be helpful to people with those types of sensitivities, then we'll have done our job. Because there are tons of people who have metal plates and screws in their bodies, for example, or have heavy metal poisoning. All of those people have been shown to have higher sensitivities of electromagnetic fields, for example, and we have an electromagnetic planet, right? So, and space weather affects that. So there's lots of stuff that just are just budding areas of medical research. And I think as we become a more spacefaring race and become more aware of space weather, it's going to get even more of the medical industry interested in actively pursuing these types of ideas. And it will also loosen up and liberate some funding for those types of things, because it's no longer going to be seen as some fringe thing. It'll actually be seen as something relatively important for our daily lives. So all of that is coming, and all of you are helping me create the possibility for all of that coming. So thank you very much. Okay, so I'm trying to say, yeah, versus Elon Musk. No, hopefully not versus, along with. I'm not trying to, as I've said before regarding Elon, we need people like him who are kind of charging forward with, no holes barred and not letting anything stop him, and maybe even being a bit cavalier in his approach. We need people like that then can be counteracted by people like me who are saying, whoa, Elon, slow down, hang on. Have you considered this? Okay, and be careful of this. And so I help rein him in. But if we don't have people that push forward that way, and we have everything run by scientists, we'll never get anything done, because according to scientists, nothing is ever ready, right? If you have launches done only by engineers, a launch vehicle will never be ready to launch, because there's always going to be issues. Same thing with looking at scientific endeavors and medical things. If you have a doctor saying when it's safe for an astronaut to go into space, no one will ever go into space, because it's never going to be safe, right? So we need people like Elon Musk who say, be damned the consequences, I'm going. And then it's up to the rest of us to kind of balance that, free spirit, and try to, and between all of us, we end up creating the checks and balances that allow us to go into space but go successfully with very little collateral damage, hopefully. All things, fingers crossed. Okay. Yes, Elon is changing the world. Yes, trust me, he has lots of help. But yes, he's one of the pioneers, and we love him for it, helping bring us into the 21st century. Okay, looks like I've answered all those questions. So looks like everybody seems to understand what's going on regarding the floppy hat, the ballerina skirt, and all that kind of stuff. So let me add one more wrinkle to that ballerina skirt picture, and that is the roll of the Parker spiral. And this can be a little bit complicated to explain, just simply because it involves both parcels, both the plasma, the particles that are moving outward from the sun, and the magnetic field spider web that threads it. Okay, so let me take a sip here. And when we talk about the plasma, we talk about the solar wind blowing out from the sun. Realize that the sun is, it's a big explosion, right? Gravity kind of keeps most of it in, right? So it's a big pressure balance, right? You've got the sun exploding all the time, and it's trying to blow itself up all the time. But because it's so massive, gravity pulls it back together, and it's this tug of war between these opposing forces. But there is some part of the sun, of the stuff that's exploding off, that manages to reach escape velocity. Okay, and that's the corona. That's the solar atmosphere. You have this tenuous atmosphere that is continuing to blow off the sun, and some of it does actually blow off fast enough to escape. Okay, and as it's escaping, it's blowing off the sun radially, meaning straight toward you in all directions. So straight toward you this way, or if I'm turned this way, straight toward you this way. So it's, blowing out in all directions equally, okay, for the most part. However, the sun, it's rotating all the time, right? It's spinning. So as it blows out a piece of solar wind, or a parcel of, let's say it blows out, we'll call it a parcel of solar wind, just a little bag of it, poof. Okay, and it's blowing off this little bit of solar wind. The region that it blew it off from, let's say, is right here. But as that parcel continues to go off this way, the sun is rotating. So let's say in the next day, the sun is rotated this far. So now that source region, what we call the source region of that solar wind, has rotated to here. But that solar wind is still going off in that direction. Okay? And then let's say it blows off another parcel of solar wind, and that's going off in that direction now. And it rotates even further, and then it blows off the next day, another piece of solar wind, and it's now going off in that direction. So in just a few days, the same solar source region, this little hole that I have, this little, part of the sun, it blows off solar wind all the time in different directions as the sun rotates. Okay? Now that solar wind is constantly going just straight out from where it blew out, straight line, right? Just because this source region is rotating around doesn't mean that solar wind is rotating around. No, it is simply blowing straight out at all times. But that solar wind, that little parcel, is threaded by a magnetic field that must chase back to that same source region. Okay? So it's like you imagine threading a needle, in a sense. As that sun rotates, that thread is pulling. Okay, it's still kind of, it's pulling the thread out, but that solar wind is still blowing out that way, right? And this is rotated to here. Well, that magnetic field line from that parcel still has to trace back into here, to this source region, because it's all connected. Okay, so you can imagine as these parcels are being blown out, you have a magnetic field line spider web that's threading through all of them and threading all the way back to the source region on the sun. Even if by the time you get, a week away or 2 weeks away, that source region's on the back side of the sun, and that parcel that it blew out is on the front side. It's still connected by all the same magnetic field. Okay, so how does that work? Anyone ever seen, and if it were one of my classes where I could see you back, I'd say raise your hand if you've ever seen a sprinkler, one of those spiral sprinkler heads that spit out water as the little sprinkler head spins. Anybody seen that? I don't know if you can raise your hand in the chat or say, yes, I have, or anything like that. But those sprinkler heads, as they spit out the water and they're spinning, you ever notice the path that the water traces becomes a spiral? Have you ever seen that? Right? Okay, and I should add a picture of it. Well, keep that in mind, okay? That is exactly what we're about to talk about, okay? So I'm going to stand. Let's see, where can I stand? Where's the best place to stand? No, I'll stand over here. Okay, so let's keep that idea in mind as I show you. Get my hair out of my face here for a second. Okay. Ooh, a little warm. As I show you the sun. Now this is, we're looking down. And why did they do it? Okay, yeah. We're looking down at the North Pole of the sun. Okay, and they're showing, this arrow is showing a direction of rotation of the sun. Okay, good, wonderful. I see people's with their thumbs up and hands up and stuff like that. Good. A lot of people have seen that. Awesome. Okay, cool. So let's talk about, it's almost as if you're going to be looking down at one of those sprinkler heads from the top of it. Okay, so the sun is rotating in this direction, right? And as it rotates around, let's say when that solar source region shoots out a plasma parcel, and you're seeing it way out here. By the time the sun is rotated around, that plasma parcel is way out here, okay? But the one after it rotated a little bit, it shot out another one here. And it rotated a little bit more, it shot out another one here. And all these plasma parcels are always moving away from the sun. And it shoots out another one here, and it shoots out another one here, and here, and here, right? And so by the time it's rotated to here, and that solar source region has rotated to where you see this, whoops, let me get my hand out of the way, where you see this white arrow. Oops, come on, Tam, get your finger in the right place. That right there, that's where the source region is now. It's about to launch this parcel of plasma. You have all these other plasma parcels that it's launched a week ago, 5 days ago, 3 days ago, you know, basically 1, 2, 3, 4, 5, 6, 7. Obviously we're simplifying it. But they've all been shot out radially, and they're all traveled a certain distance from the sun, radially from the point they were shot out, okay? But now you have to have a magnetic field line that threads from that source region on the sun through all of them. Look at the picture it draws. See the spiral? That's the same thing that you see with your eyes when you look at a sprinkler head that's spinning and you see the pinwheel of water. And you're like, whoa, it's creating, is that water curved? Is that water going along a curved path? Is that water stream really bending? No, of course it's not bending. But it's a function of how a rotating source region, as it spits out stuff, what it ends up looking like. It does create a spiral, but where the spiral comes from is the fact that it spit out each one of these pieces of whatever it is, water, solar, wind. It's spitting out these pieces all the time, and it's spinning. And each one of these pieces left the sun at a different time, or left the sprinkler head at a different time. And it appears as if it creates a curved stream. Okay? So this is what we begin to say is the Parker spiral. Okay? Now remember, again, and you'll see that the term up here, frozen in flow. We often call it frozen in flux. What that is, that's that jailing again. The magnetic field and the plasma, they're linked together. The magnetic field jails the plasma. The plasma cannot move without that magnetic field. So in a sense, they're frozen in together. That's the actual jargon term. We call it frozen in. Okay? So that magnetic field is frozen into that plasma. Wherever it goes, it takes that magnetic field with it. And that magnetic field is connected to the sun. So that's how you get that spider web. That's how the sun creates the spider web. Okay? And that spider web is created irrespective of whether it's in the ballerina skirt region or it's up in the open field lines in the fast solar wind that blows out. It's creating magnetic field spider webs that are connecting all these parcels of plasma all the time. I thought I had a different, yeah, let me see. So I'm going to show you just multiple different versions of it. Yeah, okay, I'll show you this. So let me stand on top of, let me stand on top of this one for a second. So I'm just going to show you different versions of the same kind of thing to kind of help get your mind wrapped around it. So this is the same kind of idea. Okay, you have, again, now you're looking at the sun in this direction. Okay, and the sun is rotating this way, right? And you can see, here's where the source region was. Whoops, boop, 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 boop. Get my hand in the right place. There we go. Here's where the source region was when the sun launched that first parcel of plasma. Okay? So it launched out that first parcel of plasma, you see it up here, right? And then the sun rotated, and then you get parcel number 2. That's over here somewhere. And then its sun rotated, you get parcel 3, parcel 4, parcel 5, parcel 6, parcel 7. By the time you get over to here, to parcel 8, which hasn't quite left the sun yet, that same source region that was pointed out over here, okay, that same source region has rotated all the way over to here. But that magnetic field line has created this spiral. Now imagine that not just happening here, right? But imagine that happening all over. No. Stand on this side. Imagine not just having one source region. Imagine having a whole host of them. See all these lines going out? All the black lines going out radially. Those are the parcels of plasma going out from the sun. So imagine with every of these black lines, that is traced back to a source region on the sun. Okay? See these, so you have 1, 2, 3, 4, 5, 6, how many lines are there? 1, 2, 3, 4, 5, 6, 7. So we have 7 different source regions on the sun, depending upon what part you're looking at. Right? Okay? And each of them was launching a parcel of plasma. So if you do that, you have, on day 1, you launch a parcel of plasma. On day 2, you're launching another parcel of day 3. So as you move out in time, parcel 7, this, they probably should have numbered it the other way, but parcel 7, this is like the 7th day. This parcel has gone the furthest out, right? And then parcel that, if you follow that red line, that's that magnetic field line that goes in, you see parcel 6, parcel 5. As this sun is rotating through each one of these steps, it's launched a piece of plasma out, and you can see the magnetic field threading through the first one. Whoops, it goes all the way to, sorry, over to here, right? That's that first, that's that outer magnetic field line. But if you imagine all of these regions launching parcels of plasma in their radial direction, but every single day it's turning, then this is the pattern you're going to trace out. You're going to trace these parcels of plasma going like this, with the magnetic field lines going like this. Do you begin to see the pinwheel? I don't want to belabor too long. I could spend a lot of time on this diagram, but I don't really want to. But I could take a lot of time explaining it. But hopefully I explained it far enough. So each one of these is from a different solar source region, those red magnetic field lines that begins to create that spider web. And you start seeing how these spirals are created, okay? How that pinwheel is created. And if you do that all the way around the sun, this is what you get. You get the sun in the middle, right here. Up, back. Right there. Okay, there's the sun in the middle. And this blue outer circle and the straight radial lines are to show that you've got plasma being blown out straight from the sun in all directions. But the magnetic field that threads all of these is the spiral. Okay? So particles aren't moving in a curved line. They're moving straight out. But it's the magnetic field, the spider web, that's the spiral. Get that? Okay. And we've already gone over this. See, this is where I should have, this is the plot I needed when I was talking more about the heliospheric neutral line. So I've got to revisit how I organize that. Really, in this case, what I was beginning to talk about here had to do with how that ballerina skirt, how that Parker spiral shifts and changes over the course of the solar cycle. So we've already talked about it, but that's kind of what I was beginning to highlight here. is that Parker spiral is not just flat and equatorial. It actually will shift and undulate depending upon the solar maximum or solar minimum or declining activity, right? What we already talked about. So just keep that in mind, that this platter, this disc, is not so flat. This is part of that sombrero hat, okay? But it's undulating and it tilts, okay? And the effect is the diagram I showed you before, which is the ballerina skirt. So now, as we talked about that sombrero hat, not only does it tilt and undulate, but now you see the effect of the pinwheel. Do you see the pinwheels coming out? Right? And that creates these waves. Okay? And if you have a planet now that's sitting out here, as we talked about before, right? As this thing expands outward, remember all those particles are expanding outward, right? And they're going out radially. This ballerina skirt expands outward and it keeps spinning. The sun keeps spinning, so that pinwheel keeps regenerating itself over and over again. And it just keeps moving outward and outward. What you see as a planet is you get hit by waves and waves and waves of this, okay? But remember what's in those waves, right? Fast and slow solar wind. In the sheet, you're getting the slow solar wind. Out of the sheet, you're getting the fast solar wind, okay? So here's the interesting thing, and this is where it gets a little bit complicated. That pinwheel shape will move inward and outward depending upon how fast that solar wind moves. So you can imagine, here's the diagram. Let me see if I can stand on the right side. No. Here's the diagram that you saw before, right? But realize that those pinwheels, really how curved they are dictated by how fast that solar wind is moving out. In other words, if that sun is able to rotate a lot, but the parcels aren't moving out very fast, then that solar source region that may start here, by the time it gets over here, the solar wind has only moved out that much, which means that magnetic field is really far around to get to where that other plasma was. If fast solar wind by this here. Okay, so here's the sun, and we're showing basically the same solar source region, and what you're looking at are magnetic field line traces. But you're looking at it for different speeds of the solar wind. You can see 400 kilometers a second, the slow solar wind over here, up to 1,200 kilometers a second, very fast solar wind. Typically, solar wind this fast is oftentimes a coronal, a solar storm launch, but sometimes you can get it that fast, especially at the poles. You can get wind that's really fast during really high activity cycles. But at any rate, and so we've got here, what is this? Earth, Mars, Jupiter's out there. These are the orbits. So you've got brown, that's Jupiter's orbital location. Earth and is in blue. Uh-oh, did I lose my? Hey Jerry, is microphone jack?
I don't know what it is though. As you bump it, you're cutting in and out.
Oh, uh-oh.
You're back on now.
Okay.
I guess be careful not to touch it. It may be your cable.
It's yeah, it's probably because it's broken. So I will be more careful. I am being told right now from Jerry that my microphone is cutting in and out. So thank you. Thanks, Jerry. I appreciate it. See, this is why VIPs are so important. I'll keep calling me if I mess up, but I'll be paying much more close attention. Do I need to go over more stuff?
No, we only lost maybe 15, 25 words.
15, 25 words. Okay.
Yeah.
Oh, okay, so not too bad. I'll probably end up saying it again because I'm talk a lot, so I hear myself in the background, so it's kind of funny. Okay, so I will slow down and be more careful, and I'll pay attention to the mic a bit more. Okay, thanks so much, Jerry.
All right.
Okay, bye. All right, thank you. Thanks, Jerry. Appreciate that. Sorry about the mic, guys. I do have to get this fixed, so I'll just try to be a bit more careful as I move around. But yes, I'm sure I'll get another call if things go bad. So hopefully you guys have heard that what I'm talking about here is how those pinwheel arms are the curvature of those pinwheel arms are dictated by how fast the solar wind speed is. So if I talk about the sun here with the same source region, and you can see the blue, whoops, let me get the yellow sun here. The blue region, or the blue circle, that is the orbit of Earth. Then you have the orbit of Mars in red, and then out in the very far back you have the orbit of Jupiter. That's in like tan, okay? But here in the black, you're seeing those pinwheel arms of the magnetic field moving out, okay? Notice that for the slowest solar wind, that means the parcels are not moving out very far compared to the solar rotation. When the parcels of solar wind can't move out very fast because they're slow, that pinwheel will be very tight. Okay, that's this stuff here. But if you have really fast solar wind, that means the solar wind can blow out really far, and by the time that sun rotates a lot, and that pinwheel will be a lot less curvy. The angle will be a lot less tight. See that? So on top of all of these other complications, you have the sombrero hat, you have the pinwheel arms, you also have how tight is that pinwheel, how tight in, tightly curved, or how loose it is. Okay, there's all of these variations. I bet you never expected the solar wind to be quite so complicated, did you? But you have all of these different variations in the solar wind that that contribute to making it extremely complicated as it blows out toward the Earth. So if you get that idea, then you can see how, and this is just another picture. I wonder if I have a movie. No, I don't have the movie here. No, I don't have it here either. I'll show you a movie next time. But you can imagine how now just the solar wind in of itself can be complicated enough to cause solar storms, because you can have slow solar wind being slammed by the fast solar wind ahead of it, and in doing so, suddenly you get, it's kind of like throwing a stone in water. You get these waves and they ripple because you get water that's moving very, very fast hitting water ahead of it that's standing almost still. And it creates this big steepening, this big wave and a big compression. And when you feel that, you actually feel that as a wave. Well, Earth feels that too. Earth feels that when it hits this stuff. And here's probably where I'm going to stop today. But this, I like this diagram because it kind of gives you a real basic overview of, I'm looking at the time, a real basic overview of everything that I've talked about today. That if you have the sun, and if I can get out of the way, maybe I'll stand over here for a second. If you have the sun, right, and you see that red magnetic neutral line on the sun and how I've made it all kind of undulating, right, on the sun. If you extend that out in the solar wind, and we're just doing a cut through the north-south cut of the solar wind, you see how that undulation of that ballerina skirt, this is the current sheet, okay, that kind of goes up and around. And you take this solar wind that's coming out of the sun, and it's blowing out in this direction and expanding. This is these lines here are showing basically this kind of how solar wind expands in a spherical geometry. It always expands out like this, kind of like a pie, okay, because it's got a spherical symmetry, so it's going to expand that way. So as it expands out like that, you're going to have near the current sheet, right, near the middle of this ballerina skirt, you're going to have slow solar wind. Right, we already know that. We've learned that. Of course, near the poles. Did I lose my audio again? Yeah, I must have a short now. Boy, I wonder if that cut a wire. Goodness. Wow. Okay. So up at the poles, you're going to get fast solar wind, right, at both the north and the south. Okay. But near this heliospheric current sheet, you're getting that slow solar wind coming in. But if you are a spacecraft, and now I'll try to stand here at the edge. If you are now a spacecraft that's sitting essentially in the ecliptic plane, in the middle, right, where all the planets are. And this wind is blowing against you, right, and passing you. If you notice, you're going to see like fast solar wind here, for example, when you're far away from that heliospheric current sheet. Look how high that current sheet is compared to where you are, if this is you, okay? This is you here. So you'll see fast solar wind here, and then you'll pass through that current sheet as it blows past you, and you'll get slow solar wind, and then you'll get back into the fast solar wind again. That's another fast solar wind stream, and you'll pass through that current sheet again, and you'll get slow solar wind. Remember, I'm just moving my hand across this. We're not getting closer to the sun. All of this stuff is blowing past us, and the sun keeps regenerating this over and over and over again. It's generating it as the sun is rotating, as those spiral arms are coming out the pinwheel, as that ballerina skirt is being created. So, and that's as that neutral line on the sun is basically extending into space and becoming this whole dynamic ballet. This is really, when we talk about the quiet solar wind, this is what we mean by the quiet solar wind. And so from this perspective, I think you can finally see that the quiet solar wind isn't so quiet, is it? And this is why we can actually get solar storms from fast solar wind. This is why back at the beginning of this lecture, and at the beginning of all my courses, I show you the basic 4 types of solar storms or space weather phenomena you need to worry about. And one of them, which is the coronal holes, all it does is just create fast solar wind. And you'd think that that would be very benign, but in actuality, it's not, because of this structure behind me. It's very, very complex, and it can create very, very strong solar storms, as strong as if you had a real solar storm eruption. People don't realize that just the fast solar wind can create that if the conditions are right, okay? And you saw from, a few slides ago when I talked about the solar cycle changing. Well, there are certain times when this kind of structure is far more prevalent, and that's during the rising phase and the declining phase of the solar cycle. During solar minimum, not so much, right? Because this current sheet is pretty much sitting, that red line is pretty much sitting at the equator all the time. And so we're always in slow solar wind. But here, when you have the undulation of that big ballerina skirt, you get slow and fast wind streams. So when you see me in my forecast say, we have some fast solar wind coming from a coronal hole that's rotated into the Earth strike zone. How many times have you seen me say that? Right? I can say it in my sleep. It's because this is what's happening. We've rotated, the sun has rotated in such a fashion that the neutral line is no longer, the main neutral line of the sun is no longer near the equator, and the ballerina skirt has moved, has come out to Earth's location. Okay, the ballerina skirt, where that source region is, that's kind of close to the right, to the west limb of the sun, that region is now, because of the Parker spiral and because of how the solar wind is blown out, where it's finally reached Earth. If I go to here, yeah, let me use this one. So if I talk about, if this is where Earth is, here, the plasma left the sun 7 days ago, right? Here we go. Let's say that's where Earth is. If you always wonder why, in my forecast, I show you that the coronal hole has to reach almost the west limb of the sun in order to, it reaches the edge of the sun, in order for us to see the fast solar wind that comes from it. The Earth strike zone is going to be near the west limb of the sun because of exactly this process. The solar wind is shot out when that coronal hole is facing Earth, but that's not when it reaches us. It has to travel to Earth. And by the time it travels to Earth, the source region that caused it has rotated to the western side of the sun. So that's why when you say, well, why in her forecast does she always talk about the Earth strike zone for fast solar wind being to the west side of the sun? Why isn't it right at the middle? Well, it was. When it shot out that fast solar wind toward Earth, that coronal hole was right at Earth, but we don't get it then. We get it 3 to 4 days later, or maybe 2 days later, depending upon how fast that solar wind is. So depending upon, how long it takes, how fast that solar wind is moving, if we get that high-speed stream and it's not that fast, well, that source region will have rotated almost completely to the west limb in order for us to actually see it at Earth. Whereas if it's really fast solar wind, you'll see the Earth strike zone isn't quite so far to the west limb. So like earlier in the solar cycle, this is just kind of an aside, earlier in the solar cycle, like the beginning part of the declining phase, if you look back at some of my old forecasts, you'll notice when I talk about the Earth strike zone and having a coronal hole that rotates into it, it's only about halfway between the Earth-Sun line and the very west part of the limb, the very edge of the limb of the sun that you can see on the west. It sits right about here. You'll see it about halfway. Whereas as we got closer to solar minimum, those coronal holes have to rotate almost all the way to the edge where the west limb is before I say, oh, it's in the Earth strike zone. And the reason for that is because I know those fast wind streams aren't as fast anymore. So the sun rotates even more, and that source region rotates even further to the west limb before that fast wind actually reaches us. So the Earth strike zone is actually a movable quantity. It's actually a movable location on the sun, and it all depends upon how fast the solar wind is, the solar wind streams are that we're going to be getting. And it's all due to that Parker spiral. So hopefully that makes sense. And I'll leave it at here. And I think this is where I'll leave the lecture today. We've gone about 2.5 hours, and I wanted to save some time for Jack, who had asked me to talk a little bit about geomagnetic storms. But I want to, as we go into the next lecture, I'll just mention it into part 2 of this. Hopefully I'll have my mic fixed by then. I will go into Ulysses. I'll show you some of how that solar wind changes, how the dynamics of the solar wind changes through the solar cycle, and give you a real interesting understanding of how that really works when it comes to how it really works in terms of hitting Earth and space weather, for example, and how persistent some of these coronal holes can be. For example, here's one from just about a year or so ago. We had the same coronal hole rotate 6 times around Earth. From August 12th, we saw it again in September, in October, in November, twice in November, and then again on December. And it brought storms with it, or near storm conditions, every single time it rotated into Earth view. So it's a very, this was just in, I think, 2019. So I'll go into why that is and how that happens. And I'll also give you a better feel for how the solar cycle works. I know I kind of went into it a little bit today, but we'll save most of that till next time. So let me just stop here and ask for questions. I'll keep this up so everyone can take a look at it. Good. I'm so glad, Frederick. I appreciate. This was a little bit out of sorts. I had forgotten I had rearranged some charts, so it wasn't as smooth a presentation as I wanted, but I'm so glad it sounds like it was clear, and that makes me feel good, even if it were clunky and I've got a mic that's cutting out on me. Any questions, guys? Please feel free to ask. There is no such thing as a stupid question, especially when I mess up the charts like I did today. I would rather take more time and explain and have you guys walk away feeling confident that you understand the stuff I've presented than having you, scratch your head and just leave. So please, because I guarantee you're not going to be the only one asking that question. There'll be other people having that question that are waiting for someone to be brave enough to ask it. So please feel free. Thank you, Julia. Thank you. Oh, good. Adrian, glad to see you here. Tamitha is ace. Thanks so much, you guys. I'm so glad. It sounds like everything was clear, huh? Oh, I know. InfoDog. I'll just be happy when we get to better HF propagation. I agree. Gosh, it's slow, isn't it? Okay, Sukuri, is there a return flow to the current sheet There is with the magnetic field. And yes, the electric currents, they close, but they don't close here. They close on the surface, the edge of the heliosphere. So you have to go out basically to the heliopause in order to get the closure for some of these currents, because that's where the magnetic field closes up. Because the sun, as it blows out the solar wind, it'll blow out the solar wind, but as it blows out, that solar wind expands in this bubble. And as the bubble continues to expand, the solar wind weakens. The pressure lowers because it's getting bigger. So as the surface area is expanding, the pressure has to kind of die down, and eventually it gets to a point where it can't stand off the pressure from the intergalactic flow, right? The flow of the Milky Way. So that is where we end up getting a heliopause. This is where we end up, and there's a whole, I actually have a whole class on this that we will go to, we'll get to maybe after the coronal hole stuff. It depends upon what the Patreon audience wants to do. But once we get to that heliopause, once we get to that bubble, there actually is a, believe it or not, a termination shock and all this other kind of physics that goes on that prepares the heliosphere to be able to kind of stand off the flow as we move through the Milky Way, because we are moving through the Milky Way, and there is we actually have to divert some of the sun's solar wind behind us, so we form a comet tail, very similar to what I'm going to talk about here shortly with the Earth's magnetic field and the Earth's magnetic shield, how that gets diverted into a comet tail. Similar to a comet tail because of the solar wind. So the same thing happens to the sun's solar wind. It gets diverted into a comet tail behind us, behind the sun, behind the solar system, as the solar system is moving through the whole Milky Way along its spiral arm. It's a really neat process, but yes, currents close, magnetic field closes, everything is self-consistent. It has to be. So yeah. Great job. I was able to understand the material. Fantastic. Thank you, Joseph. It makes me feel good because I don't feel this was my best presentation. I think I just was too worried about this microphone. Definitely a bit off balance today. Let's see. Does a particular parcel of solar wind move only radially? Yes, it moves only radially. Believe it or not. It's the magnetic field. I mean, there'll be wiggles and stuff like that, but it literally is moving out radially. How it shifts back and forth or things change or something like that depends upon what other junk in the interplanetary medium it comes across. If it hits slow solar wind or goes through a shock wave, something like that, then yeah, it'll be the dynamics. All bets are off. Things change. If a big solar storm plows through it or something like that, yes, things, again, all bets are off. Things will change. It will have to divert itself. If a planet is in its way, yes, it's going to be changed. There's all sorts of physics that occur to divert that parcel of solar wind around the obstacle. Same thing as, the air is going to move out of the way of a baseball as it's coming at it. So it's the same kind of idea. A lot of the same principles apply. But in general, the solar wind being unobstructed by anything else in the solar wind, it will continue to move out radially with very little change in that sense. And it shoots out, radially, depending upon where its source region was, it'll shoot out. If it's shooting out along the ecliptic plane, it'll stay that way. If it's shooting out along the poles, it'll go up north. Oops, there goes my mic again. It'll go up north or it'll go down south, that kind of thing. So it's definitely mainly a radial phenomena. Let's see, okay. Okay, let's see, the chart of the magnetic field of the sun that you had in one of your slides, does the Earth's magnetic field have the same appearance as the sun? Not quite. The reason why, I mean, it's really the time scale is why we don't see a lot of the similar things. Obviously, the thing that causes the Earth's magnetic dynamo is a totally different process than what causes the sun's magnetic dynamo. The Earth's magnetic dynamo has a lot more to do with the iron core, and actually, if anything, the transition region between the solid iron core and the liquid iron core. It's this slushy region in between where it's kind of like an icy of iron. If you can imagine that, how many thousands of degrees. But the Earth's magnetic dynamo is definitely generated by, you've got the rotation of the planet, but then also iron core that is cooling and sinking and then heating up and melting, and the convection patterns that are going on in there along with the rotation of the Earth creates the magnetic dynamo. In the sun, we believe that the magnetic dynamo is actually created much closer to the surface in a thin layer in the convection region. Do we understand that process? No, we don't. But we see flows and patterns that that, and we've been able to have dynamo creation, models that have created rudimentary dynamos. So we know it is possible, but we don't really understand it. However, realize that, the Earth's magnetic dynamo does flip, right? The dipole field of the Earth does flip just like the sun's does. It just does it on a much slower time scale. So when I show all of these magnetic field models of the sun, especially ones that show like a multipolar sun where the dipole field is flipping during solar maximum, oh my goodness, very rarely does the Earth's magnetic field look like that. I will do a talk at one point on the fact that our field is beginning to flip, and really what's happening is very similar to what does happen on the sun every 11 years, which is the dipole component of that field is flipping, but that's just going to reveal smaller components, or what we call higher order terms of the dynamo, meaning the quadrupole field, the octupole field. These are smaller components, not as strong as the dipole field component, and obviously the dipole field component has two poles. The quadrupole field has 4 poles. So as the dipole field of the sun, of the Earth flips, and it goes to 0 for a short while, the dominant component of our Earth's magnetic field will be the quadrupolar field with 4 poles. So guess how many poles we're going to have? We're not going to have a north and a south. We're going to have like a northwest and a southeast and a northeast and a southwest pole kind of thing. And they're going to be probably, more at mid-latitudes than just north and south. But that will be a temporary situation, and then as the dipole field reforms, just like the sun's field reforms, the dipole field will have flipped. North will be south and south will be north, but we'll go back to a dipolar configuration. It's just that with Earth, it's definitely not 11 years. It's hundreds of thousands of years, right? So that process is so much more slow that really when you say, is it the same? Well, there's aspects of it that are similar, but there are a lot of aspects that are different as well. One thing that's going to be very interesting I'll mention is in space weather, when space physicists and magnetospheric physicists, those are the people that study the Earth's magnetic shield, when they decide to focus more on what the near-Earth space environment is going to look like when our dipole field flips at Earth, because it's going to decimate the radiation belts, right? The Van Allen belts are going to go away. There's no way they can survive. The magnetic field configuration is so crazy looking as the field flips. I've seen a couple models of it. UCLA has a couple really good models of it where they show the magnetic field. It looks like taffy pulling. I mean, the magnetic field lines are just everywhere. I look at that and I say, how can anything stable, any stable radiation belts even exist during that period? I don't know. I think it's going to be a fascinating field of study when people find it, important enough to start migrating some science resources and assets toward solving that problem. I don't think we're there yet. I think there's a lot more low-hanging fruit that people would rather chase. But I tell you, it's going to be a fascinating field of study once it ramps up. So thank you for that question. That was really good. Let's see. Could there be a plasma at the core of the Earth? No. Everything's neutral there. A lot of things are radioactive. We've got radioactive activity in the core. So if there is plasma, and everything's so collisional that once you get collisional plasma, things become neutral really fast. One of the reasons why in space things can remain a plasma for so long is because there's no, at such low energies, let me put it that way, is because there's no way that these particles can recombine with other particles because they can't find each other. All they have are magnetic and electric fields. They don't, remember how I talked about it takes basically from the distance from the sun to the Earth for one particle to even hit another one. So if you're alone and you're an ion, or you're alone and you're an electron, you're going to stay an electron, right? What happens in Vegas stays in Vegas. You're not going to be able to find any way to change. So you're just going to stay like that. And that's one reason why the solar wind is like that. Another reason why in space particles stay that way is because the sun is always irradiating them with ultraviolet light. And ultraviolet light loves to split electrons and shear electrons right off of atoms. It's the photoionization is what we call it. And that happens all the time. So really there aren't many neutral particles, if any neutral particles, floating around in space at all. At least not in our heliosphere, that's for sure. There's some dust, but not much. Pretty much everything is ionized. But in the core of Earth, everything's touching each other. So if you create a plasma, it sure won't last very long. And I'm sure there are ionization tracks because of the radioactivity of the Earth's iron core. So yes, there are ionization tracks. So you create ionized particles for just a moment, and then everything rushes in and recombines and fixes itself and glues itself back together. So nothing lasts probably, I'd be surprised if things last more than microseconds, probably more like nanoseconds before things, calm themselves down. But that stuff's happening all the time. But you need to really, look at radioactivity and radiation bombardment and stuff like that to understand more about at least the details of that. Hopefully that answered that question. Let's see. Does the wiggle and speed of solar wind create electromagnetic radiation? There are a lot of electromagnetic processes that occur in interplanetary space. As a matter of fact, there's magnetic reconnection in interplanetary space. And Jack Gosling, God rest his soul before he died, was looking a lot into reconnection in the solar wind, looking at Alphane wings. And we see evidence of reconnection because it's really hard to find, pass right through reconnection regions where all of this stuff is taking place and reconfiguring. But in the solar wind, in the Earth's magnetosphere, in the Earth's magnetic shield, for example, there's all sorts of processes that are happening like that all the time. Mainly because the particle how do I say this? We have lots of groupings, lots of, I want to say distributions of particles. There's lots of types of particles in the Earth's near Earth space that are very, they're unstable. The only reason why they stay that way is because the Earth's magnetic field forces them to be like that. And these particles are always looking for ways to escape or smooth out, what we talk about with entropy. So there are always wave processes going on. I mean, ion cyclotron, emic waves, chorus waves, dawn waves. We have all sorts of different processes that are occurring all the time. Some of these waves even make aurora, because they shoot particles down into the Earth's upper atmosphere. But all of these are electromagnetic processes. And for example, electric field instruments on spacecraft in the Earth's magnetic field or in the Earth's magnetic shield area, they're very telling because they show when certain processes are growing and when certain wave activity is happening. And these are all electromagnetic wave activity. And depending upon the type of wave activity we see, we know exactly what's happening to that particular plasma, whether it's being isotropized or energized or some type of instability is occurring. There's multiple fields of study. You could get multiple PhDs in all sorts of little regimes inside the Earth's magnetic shield, studying nothing but waves. Your whole doctorate dissertation could be about waves, and you still wouldn't know everything there is to know. But there's a lot more of them going on, a lot more interesting ones going on in magnetic systems like the Earth system or the Jovian system. In interplanetary space, yeah, there are waves and stuff going on. It's a little bit more boring, though. Just because the solar wind is much lower intensity and it's not configured nearly as crazily as it is inside the Earth system. Plus, when you have a big geomagnetic storm at Earth, boy, the Earth's magnetic field wiggles and changes and causes all sorts of crazy stuff to happen. So that makes it even more, that makes even more wave processes occur that are much more exciting. So hopefully that answered that question. What is the difference between low and high proton density? Let's see. Well, low and high proton density, what do you mean, what is the difference? Other than the density being low or the density being high? More particles in high density stuff, less particles in low density stuff. And if you're asking me what are the relative amounts, well, it depends upon what the process is that you're looking at. A low density solar wind, for example, just solar wind, low density solar wind could be, I don't know, maybe 4 particles, 5 particles per cubic centimeter. Not very much. High density would be, I don't know, 30 particles per cc. You get into a solar storm, you may see, God, really intense one, you might see spikes of 100 particles per cc. Not typically more than that, Maybe a Carrington event or a big filament might get you a little bit more than that. You get squished by, a shock, some fast wind and slow solar wind hitting. You can get some pretty intense spikes, but usually, maybe a couple orders of magnitude change at most. Usually 1 order of magnitude change, so by a factor of 10 or so. But, once you go inside the Earth's magnetosphere, the Earth's magnetic shield, you can get a lot bigger changes than that, huge changes. And off the top of my head, I can't give you numbers because I'm not a person who studies a lot of processes inside the magnetosphere, so I don't have those numbers memorized. I'm a person who studies the sun and everything coming up to the Earth's magnetic shield. I know the processes that occur inside the Earth's magnetic shield, I just don't know them as intimately as, let's say, a magnetospheric physicist would. So I can find those numbers for you if that would answer your question. But hopefully if you have something else in mind and I'm missing the point entirely, please restate it in the chat and I'll get to it. I know I might have missed a couple, but let's see. The Earth may be neutral overall, but there are electrical layers that have charge as evidenced by the ionosphere and plasmasphere. Yeah, that's true. As you go higher and higher, you have the neutral atmosphere down below. It's kind of protected, but as you go higher and higher in the Earth's altitude or in Earth's atmosphere, those layers that get further and further out, you're now getting a lot of penetration by the sun's UV activity, and so that, once again, we talked about photoionization. That's what you're getting. The sun's ultraviolet light ionizes the upper atmosphere, and that's how the ionosphere is actually created. Now, of course, there's all sorts of other processes that help to continue that ionization, but the main source of ionization for the Earth's upper atmosphere that creates the ionosphere overall is on the day side, and that's the sun, literally the sunlight hitting it. So, all those big college words are throwing me off. I'm sorry. I'm trying not to use too many. I keep saying magnetosphere, and I mean magnetic shield. Yeah, I'm not perfect. I'm a scientist by nature, and I'm trying to not use that language. But you have to bear with me when I mess up, because my default from all the years that I've been a scientist is to use that jargon, and I'm really trying not to, and you guys have helped teach me so much in terms of how I can communicate this stuff to you without using those big words. So, keep flagging me on it, and I'll keep, working on it. But definitely don't, if you say, Magneto, what did you say? What's that word? It's too big. Tell me that. I want to hear that. So then I will find a word that makes more sense to you. It's not about, jargon doesn't indicate that you're smart. It just indicates that you're indoctrinated in a particular field. That doesn't mean you're smart. Smart people know big words and small words, and we all should just be able to communicate that stuff. I think intelligence with people has to do with what you're able to understand, and if you're limited by the language, then that's not really giving you a fair shake, right? And I think most people are very brilliant. I know you guys are very brilliant. You've stuck with me and you've helped train me. To help train me makes you extremely brilliant, because I'm not easy to train. And the fact that you help me find a way to teach this stuff to you and help you learn by getting me to use different language shows me that, how brilliant you are, right? You don't have to be a PhD to understand this stuff. We just have to find the words that work and find the analogies and the metaphors that make things intuitive. Because space weather, from a conceptual point of view, is very intuitive if we find the right language. And that's all we're trying to do. So keep calling me out on it, and I'll keep working on it. So thank you. Thanks, Text Flash Cove Installer. Wish you had a shorter name. I feel like Lilu Dallas. You have a shorter name? I'll call you Texas or Flash, maybe. Let's see. Earth will be shaken by the magnetic force of a celestial body. Will this affect the sun as well? We were talking about tides earlier. Yes, those tidal forces exist. How much effect they have is up for debate. Even in mainstream circles, it's still up for debate because we don't understand the fundamental processes that have even larger effects. Once we understand those processes and we can subtract off those effects, then we'll be able to attack the things like tidal forces. I had a good long conversation about that with everyone, probably about, I don't know, an hour ago now. So if wait till you can review this course, and you'll see that. So that's a good question because it's been asked before. You're welcome. Thank you so much. Thank you for all the work you're doing. I appreciate that, guys. Okay, cool. It looks like, excellent. Looks like we can, I'll move on for now this, now, okay, so here I am kind of stream of consciousness thinking, sorry about that. This essentially closes the whole solar wind coronal whole lecture for today. I will go into what I mentioned before. I'll go into the other stuff next time. We'll have a part 2, and we'll talk a little bit more about the solar cycle and kind of putting the picture together. And I'll show you a bit more about the Ulysses mission and how the solar wind really does change over time, and you can actually see it. I mean, it becomes very, when I show you a few movies, and I'll show you, also show you movies about the ballerina skirt, and I'll show you movies about how the ballerina skirt changes as we get to the edge of the sun's heliosphere, how it changes, and it begins to address some of those questions about the bubble, right? And it also gives you an idea of how the galactic cosmic rays can penetrate, and what makes, where is it easier for them to penetrate, where it isn't, and really how that changes between one cycle to the next. It's really kind of fascinating subject. So that's what we'll talk about in the next, in the second lecture. But right now, what I'm going to do is I'm going to go ahead and break with this and go over what I promised Jack Delacourt from my, if I'm pronouncing his name right, I forget if I am, what I promised him in my Patreon community, which is a little bit about excuse me, I can't think and change charts at the same time. A little bit, oh, come on, give me the right, hold on a sec, guys, I'm sorry. My computer is deciding to be cheeky. Please. Well, why did you do that to me? Oh, it's strange. I'll leave it. Okay. He's asked me to talk a little bit about the solar wind, how the solar wind, when it hits the Earth, what a geomagnetic storm is. And so I'm going to briefly talk about that just a little bit to give an overview. This is not going to be in depth at all, and I'm just going to be using a few charts that I've been putting together for part of my for the second course I'm doing for SWEN for Millersville. So this is just an overview. I will end up having a real lecture about this probably within the next 3 or 4 months. It depends upon what the Patreon community wants me to do. And I'll go into depth about things like geomagnetic storms compared to substorms and how they affect the near-Earth, the near-Earth environment to a great degree. You'll see a little bit of that here, but just briefly. And let me check before I do that. Let me just make sure. Hopefully my microphone's okay. I want to check to see if anyone has asked me questions. Let me go on Patreon. Let's see. Because I got all the questions from, oh good, okay. Nope, looks like we're good. I saw just comments, some wonderful comments, thank you. Check, check. You guys still hear me? I hope so. Okay, so this is for Jack, and I will play a movie, but I first want to talk a little bit just about the whole, kind of the whole picture. So I stand on this side, yeah. So one of the things that is in your future, if you guys are going to stick with me and hang out, but like I said, feel free to leave because this was the end of the Coronal Hole stuff. This is all just for some Patreon, extra Patreon people. As we take a look at the sun and we talk about, not just big coronal mass ejections, that's what this big blue blob is going out in this diagram. This is kind of like a neat little diagram that just kind of talks about space weather in general. All of this stuff, including all that solar wind stuff we talked about today, gets blown out toward Earth. Okay, there's a very complex set of events that happens. Once you hit the edge of the Earth's magnetic shield, which is this, you see here, you see this, the Earth sitting kind of right here. If I can show it right here. Notice again, notice how this kind of looks like that solar thing with a tilted dipole, right? If I rotated the image, the dipole wouldn't look tilted because you'd have it going right out this way. But notice that you do have those same elephant ears coming out like this. And the difference with the Earth, you don't have them streaming out, right? You don't have the elephant ears being pulled because the Earth is not blowing up, so there's no explosive atmosphere that's trying to escape. In the case of the Earth, you have solar wind coming in and hitting it, and it just crushes the front end, and I'll go over this more. It crushes the front end of this magnetic shield here that looks a lot like a dipole magnetic field, and then it takes that back end and it elongates it. Okay, and like I said, I'll go through much more of this in detail when I do the course on geomagnetic storms, but this is just kind of a little overview. And so I'm just using charts I have, because I don't think this is the best chart, but it helps. As that stuff comes out, there's all sorts of things that end up happening. You can have particles entering in the polar regions this way, okay, and through open field lines. But believe it or not, what people have a tendency to think is that when a big solar storm or even the solar wind hits Earth, all of that junk just slams right into the Earth shield and enters from the front. It doesn't. Believe it or not, that doesn't happen. What happens, though, is the solar wind, if it's got the right configuration, will peel like a banana. It'll peel this front end of this magnetic field off. It'll take it, it'll detach it right here. We call this is reconnection. It'll detach it and peel these field lines back and peel them this way, okay? And it'll keep doing that. And as it peels these field lines back, it's able to take that energy, and as it comes together back here, it actually takes that energy, folds those field lines back, and then shoots stuff from behind, literally from the comet tail. Let me go back here. I'm sorry, it's to show here. It literally peels all that field line stuff back and gives particles coming from the back end. And I'll show a movie that talks about that, okay? So the first thing to know about geomagnetic storms is not when you see movies or any type of description of this stuff slamming into the front end of the Earth's magnetic shield and just entering all the particles from the front end. That's not how it happens. The solar wind peels back this magnetic field to the back part of the Earth's magnetic shield, and it dumps its energy, believe it or not, in the poles, and a lot of it from the back. It's a pretty crazy thing. Very non-intuitive. Now, the Earth's magnetic shield is very complicated. And this is the main reason, if anyone wonders why, when I introduced all of these topics of solar phenomena, and I never once talked about what really happens. I mean, I went into like specific cases. Okay, here's like a Carrington event, and this is when the Carrington event happened, and what happened at Earth, what effects we saw. But I never specifically went into all of the processes that occur inside the Earth's magnetic shield. The reason for it is because, as you can see here, just from this cut of the Earth's magnetic shield, you see the sun right down here. If I go right here, okay, you see the Earth, this little green ball, if I can point to the right place. Right there, okay. The Earth's magnetic shield, and then you see all this green is kind of the outside, what we call the magnetopause or the magnetosheath region. It's a very complex thing, okay. You see kind of these weird ribbons. They're actually just showing like shells. This is a cut, kind of an oblique cut. It's supposed to be a meridional cut right through the north-south region, but it kind of looks like it's angled a little bit. It's cutting through these shells of like magnetic, I don't want to say magnetic field, but it is magnetic field. We're not looking at magnetic field lines in this case. We're looking at, I guess like contours of the magnetic field strength. And so they end up looking like shells from this perspective. But now you can see the front end in this case is, we're talking about a very small closed magnetic region. This is the dipole field. The front end is being compressed from the sun. And again, why do they do these stupid diagrams at an angle? Because it makes me have to do this. I have to like lean way down to get this to you. So the sun is driving the solar wind into the Earth in the front. It's compressing the front end of that dipole field, which is making it really small. And it's elongating the back out. Okay? The back part of that, and I guess I have to go up like this because that's the way the diagram is. Okay? So it's compressing the front, it's elongating the back, and when there's actually solar wind that is actually causing the parts of this field in front to be peeled back, it actually is peeling it back and laying it, kind of like unwraps it and folds it back on itself. So if I can do that properly without making my mic get all jagged, here's the closed magnetic field here, and if the solar wind has the right configuration, it breaks right at where my wrists are touching. It breaks that magnetic field and folds it back this way. Okay, hopefully that makes sense. You'll see a movie that kind of shows that. That is how a solar storm actually starts. But we have all of these different regions: magnetic tail, neutral sheet, plasma sheet, radiation belt, cusp regions, auroral zone, magnetopause region. You know, there's going to be a test later on this. I'm just kidding. But all of these regions, you could get a PhD studying any of these regions in of themselves. And every single one of these little microclimates, so to speak, are different. They're all different, and they all have something different happening during a solar storm. So you can imagine what a solar storm looks like inside Earth's magnetic shield. Depends upon what region you're in. So when people look at satellites, for example, in geo orbit, right, they're going through the outside of the outer radiation belt. A geosatellite will show something radically different than what the same instruments on the ISS would show, right? Because the ISS is in low Earth orbit, really close, way below the radiation belts essentially, except for one small part, which is a South Atlantic anomaly. So when people ask me, well, why don't you just show how a geomagnetic storm affects Earth, you know, from one of these big solar storms, it's like, whoa, slow down, because first I need to teach you the solar phenomena, and then I need to stop and turn around and teach you how different regimes inside the Earth's magnetic shield see storms differently. And that space isn't just space. Most people think space is space. Well, no, it's not. This is why space is hard to do. And this is what a lot of people, even in aerospace, even people who've done space missions for many years, often fail to see. They fail to realize that you can't just translate one regime to another regime and expect something that survives in one region to survive in another. Inside the Earth's magnetic shield, there are many different kinds of hostilities, and they're amplified because of what the Earth's magnetic shield is doing in response to the solar phenomena. And what you see playing out on the ground is only a fraction of what's really happening up out into space. Now, some of that activity is actually mapped down so that you can actually directly watch it. Aurora, for example, is a direct response to what's going on out in the Earth's near Earth space. But it's very difficult to look at aurora and say, oh, I know what the edge, the solar, what we call the subsolar region at Earth is doing. That region actually, which is this point right here that I'm talking about right here, that region actually is seen far more at low latitudes, not high latitudes. At high latitudes where you see aurora, that's actually what's happening closer to the cusp regions. Okay? What's happening in the subsolar region near the equator is actually more what you see going down at low latitudes at Earth, which oftentimes result in EMPs. Brett Carter, Dr. Brett Carter, who some of you follow on Twitter, talks about this all the time because, and he's written several really good papers on it about what we call the sudden storm commencement and the big compressions that we get and how it affects low latitude regions far more than it affects mid latitude or high latitude regions, whereas low latitude regions don't really see aurora unless it's a huge storm. But high latitude regions see aurora, but they don't really see the EMP, again, unless it's a huge storm. So it's to answer the question of what is a geomagnetic storm and how does it work, you can see my obvious, kind of quizzical, how do I answer this question simply? Because it gets much more complicated as time goes on. Now, what I will show you, I'll show you two different things. Let me see, which do I want to show you first? I think what I'll show you is, and I'm not going to go over the big radiation belt stuff, all my text here. What I will show you though is an example. I'll show you a movie. I'll show you that right now. A movie of kind of what I just talked about a solar storm hitting hitting Earth and really, in a nutshell, what happens. And some of you may have seen this movie before, but some of you may not have. Okay. Hopefully that's going to go good. It's going to go away. Okay, so here's the photosphere layer. This is the sun. This is the white light image, and you can see a sunspot. Don't worry, we'll get through this reasonably quickly. Here's the chromospheric layer. Hey, guess what? Can you see where the magnetic neutral line is? Can you see kind of where the bright regions are? We just talked about that, right? Here is a solar storm erupting. In this case, it's called a prominence because it's on the edge of the sun. You can see that nice little tornado thing happening, right? It's kind of neat. Once again, a proxy of the magnetic field jailing the plasma. As we move out into this, past the sun out into the solar wind, you can see those streamers we talked about today. All of those blasts are big coronal mass ejections, the big solar storms that are coming out. Here's a picture of a flare, and the reason why we're showing this, I'll just kind of let it play for a sec, but the reason why we're showing this is because we're about to show a model of what happens when one of these big solar storms is launched. And in this case, we're not going to just talk about the solar wind, we're going to talk about a big solar storm. But as one of these big solar storms are launched out into interplanetary space, it will demonstrate exactly how a geomagnetic storm begins to occur. Okay, so here's the beginning of the model now, and I'll kind of try to step out of the plane here. I think the first thing we'll show, so that's the sun. You'll see this big blob, there it is, big blob coming out of the sun. Okay, that's supposed to be like the particles. Remember, they all go radially. The first planet it's going to hit is Venus. We're going to talk about that. Notice how Venus doesn't have a magnetic shield, so the particles do slam straight into it. Okay, that's what most people think happens at Earth, but at Earth it's different. Okay, so here's Earth. Notice, can you see the particles being deflected around the planet? Can you see that? Okay, those particles being deflected around the planet, that is showing that magnetic shield. Notice that they don't hit and penetrate from the front. And that's because this magnetic shield, which looks like a dipole, you can see the North Pole and the South Pole there, and it's wiggly, it's springy, right? Magnetic field moves and wiggles a lot because there's lots of currents going on and it always tugs on the magnetic field. But if you put that magnetic shield from Earth into the solar wind with a solar storm, you're going to see it compresses, just even the solar wind, compresses that front end and pushes against it and elongates that back. Now look what happens when the storm hits, okay? See how you're seeing the field, watch it's coming in. What happens is that, oh, I gotta rewind it. It goes too fast. I can't talk through it. So let's see if it shows it. I don't think this particular movie shows the peeling back of the field. It doesn't. But I'm gonna freeze it here for just a second, and I promise I will get a higher resolution of this video. It's a pretty low resolution, but hopefully you can see. So here's the point when a solar storm is hitting the front of this shield, okay? And you can see they've got it kind of like with these particles right here. Notice they're not penetrating, okay? What happens at this point is if I were to show the solar wind magnetic field, and if that solar wind magnetic field was pointing north or southward, okay, pointing this way, the Earth's magnetic shield on the inside points northward, right here at the front end, what we call the subsolar point. If the solar wind magnetic field points south and the Earth's magnetic field points north, when they touch each other, we get something called reconnection, okay? This is when the solar wind can actually take that magnetic field of the Earth at the front of the subsolar point and peel it, open it up, and peel it back. And it peels it back, it lays it on top of this part of from the core, or the poles here, north and south. I'm going to get my hands in the right place, okay? It will open up that field and peel it back so that it lays out on top and folds back this way, okay? They don't show that particular process, but that's what's beginning to happen here. And if I play this forward just a little bit, what you see, what you're just beginning to see here, you'll notice particles are being energized. These field lines are showing these field lines lighting up both in the North Pole and in the South Pole, because there are open field lines that allow particles to penetrate in these regions. So particles begin to penetrate through the open regions and also through what we call the cusp regions, which are here, okay, here and here. These are open field regions. but also the peeling back of that magnetic field then causes a lot of energy to be dumped in this area. A lot of magnetic energy, particulate energy that's all trapped. And it causes that comet tail to stretch out further and further and further. They're not showing it because it's happening way too far back down this way. But what ends up happening is that big tail of the Earth gets so laden and so heavy, okay, that it pinches down. The pressure builds up and it pinches down. The magnetic field pinches down. And it's actually, as it pinches down, it actually causes it to break. So really, when you look at it, it almost is like you're taking that magnetic field, and as it's getting more laden and laden and laden, it's like the pressure's building up. So it's very similar to like when the sun has those streamers and it stretches out those streamers and pulls them and pulls them and pulls them. You do that to the Earth and it can only handle so much. It will stretch out that rubber band like a slingshot, okay? And when it stretches it out so far, that field pinches in, it breaks, reconfigures, and the rubber band snaps back and goes whoosh, and snaps everything forward. And that's what you're beginning to see here, right? That's what this line is here. Guess what this is? Does it look kind of like that current sheet we were talking about before with the sun, right? It's exactly what it is. This is a current sheet, okay? And it's shooting a ton of particles forward. Now, once those particles shoot to a certain point, they will then begin to follow those field lines because there's a field line reconfiguration happening. Those field lines begin to diverge and become more like the streamer of the sun, right? But it's now the tail of the Earth. See, in physics, beautiful, there's so many things that happen that are repeatable. Things we see on the sun are very similar to things we see at Earth because the physics is the same. So that doesn't mean one causes the other necessarily. So just because you see Alfvén waves on the sun and you see Alfvén waves in earthquakes doesn't mean they're direct causally related. It just means the same physics is happening. So in this case, we see something very similar to a streamer, but in this case, the particles are being shot this way. They're going to follow the field. Remember, they're jailed by the field. This is that collisionless plasma. They're following the field lines, and where do those field lines go? In the north and the south. You keep following them in, keep following them in, keep following them in, and where do they dump? Right in the north and the south poles. Aurora. These are the particles that penetrate down into the northern and southern hemispheres and cause aurora. So in a geomagnetic storm, aurora is how we get rid of the energy. As a matter of fact, some of my magnetospheric friends call the northern and southern caps, the auroral caps, the auroral ovals, they call it the exhaust pipe of the magnetosphere. We have all this extra energy, you dump it in here, you dump it in the northern and southern poles, you create aurora, and all of that lighting up the atmosphere like a big neon beer sign, and it dissipates all the energy. So you basically light the Earth up like a light bulb and burn it off. And the bigger the storm is, the bigger that auroral oval must be. The further down on the head the cap must come until you pull the cap down on the north so far it reaches the equator. You pull the cap up the south until it reaches the equator, and now you have aurora lighting up the entire atmosphere of the Earth. How big of a light bulb do you need, right? Depends upon how big the solar storm is that hits you, right? And how much energy you must dissipate, okay? So as I play this, I'm going to back it up just a little bit. You can watch that occurring. Okay, and I'll back off here. So I'll show very quickly. You see the solar wind. Here comes the storm hitting. Here goes the particles. They light up the top. They light up the inside. And you'll see the particles shoot up from the back. And then you'll see a close-up where those particles shooting up the back are now whammo. Do you see that? There they go really close into the north and into the south, and you can see they actually light up the radiation belts as well. That's why you start seeing this cloud around this region. There's the radiation belts showing it, and then you also see the lower energy stuff dumping into the Earth's atmosphere, and now we have aurora. Okay? And again, small storms cause aurora at high latitudes. Bigger storms, it comes further down. Even bigger storms, you can get aurora all the way to the equator. Okay? So hopefully that, and along with things like EMPs from compression regions, I'll go back to here, go back to the main yeah, I'll do this one. I'll freeze it right there so you can see some nice particle radiation there going in, highlighting the magnetic field, showing them shooting down the field from the tail forward. Okay. Depending upon the type of solar storm you have, how strong it is, that dictates where you see aurora. If it's just high latitudes or maybe even further down, all the way down to the equator, with the biggest storms where almost the entire globe has some level of aurora happening. You also will get from the hit of that solar storm when it first hits, and even big compressions from fast wind streams, if they're strong enough, they hit the front end of that Earth's magnetic shield and they cause a compression. And that compression is actually felt at low latitudes far more than at high latitudes, because the compression actually, if you look at where that front end, where it maps to field lines that are really, let me get my hands in the right place, it can map to field lines. All of these compression regions can map the field lines that are very, very low at latitudes, okay? Whereas stuff up here in the cusps region or in the auroral regions map to stuff at higher latitudes. So you will oftentimes, with compression from solar storms hitting, or shock waves, or big fast wind streams, you will get a compression that is actually the intensity of currents that are generated on the ground, both GICs, these geomagnetically induced currents, and also the very fast EMP caused by the shaking of the change of the Earth's magnetic field, very fast change of the Earth's magnetic field. Most of that will be felt at low latitudes much more strongly than it will be felt at high latitudes. Now, as the solar storm continues and continues and continues, you will then get GICs everywhere, right? And so oftentimes it ends up being the ground conductivity at Earth that will dictate whether a geomagnetically induced current on the ground can then affect your power grids. Some ground, like under Canada and the east coast of the United States, for example, has high conductivity, and therefore lots of current can be induced into the power grid system. Other places where the ground isn't so conductive, not so bad, So again, the problem with geomagnetic storms is that there is no one size fits all. We may have a one size fits all when it comes to the solar phenomena coming off of the sun, but once it hits the Earth's magnetic shield, all bets are off. Once it hits the Earth's magnetic shield, it becomes far more, the reaction, the effects become far more like terrestrial weather, where you have these microclimates, you have these very local responses that are very much more like terrestrial weather, from the point of view of, it may be raining in Kansas, but it's sure not going to be raining in Alaska, right? You could be having a very different, radically different, you have a dust storm in the Sahara and a hurricane in the Gulf. It's going to be very much more like that. And that's why when people say, well, why are you training? Why do you need space weather, more than one space weather center in the world? Can't one do it all? It's just one sun. It's going to be a global phenomena that hits Earth. Yes, yes, yes. But each region is going to react differently because of how complicated the Earth's magnetic system is. And the Earth's magnetic shield is just the tip of the iceberg, right? Because then we have to go to the ionosphere and even further down, right? All the way down to the ground. There are variations all over our planet. So it becomes as much a geology kind of issue, especially when you get down to the ground, as it does have anything to do with the actual space weather phenomena itself. So hopefully that helps to give you an idea, Jack and others who have asked me about geomagnetic storms. This is as far as I really want to go in terms of that. I was going to talk about a little bit more, but I think I'll save it for the more detailed discussion. But hopefully this did answer a lot of your questions. And obviously if you have any more questions, please let me know. I'll be very open. Okay, aha moment here. Oh, good, I'm glad. Yes, space weather is it's neat for that type of thing, because certain things seem like they should just be global and there really shouldn't be any local effects. But then when you see the whole system explained, you go, oh, of course, why didn't I think of that? How simple. Granted, the details aren't simple, right? But the conceptual idea of it is. And it is very much like weather. So does any of that energy affect the core of the Earth? You know, I'm probably, but again, it's one of these things where how do we measure that? How do we know? There's so many other geologic and geophysical things that are happening that are so much more dynamic and what have much stronger forces that the space weather effect. It's again, it's the toys in the bathtub. We have to drain the water out of the bathtub before we can see what toys are there. So right now we're still sitting with a full bathtub, and we have no way to drain that water and subtract off the stronger effects that are the geophysical and geological effects, for us to be able to see the kind of forces that space weather, and the role that space weather plays. I mean, we're only beginning to realize and really appreciate the fact that the ionosphere can signal that we're about to have an earthquake based on some weird, electromagnetic and density changes that occur from the ground shifting, and it signals something in the ionosphere, and we actually can see in the F1, F2 layers. I think it's in the F layers, but it may be lower. But we can see some changes up in the ionosphere that were induced by the ground down below. So there's an effect where the terrestrial weather and terrestrial geology has effect on the atmosphere. It's really cool. We've seen that for a while, but when you talk to an ionospheric physicist of why don't people chase this? Well, because it's hard. It's easy to go back and see it from a forensics point of view after it happens. We can even see effects of tidal waves on the ionosphere that can kind of forecast that stuff. But because the wiggles are so small compared to some things, they're really hard to pick out unless you know what you're looking for. So it's easy to do it after the fact. It's kind of like, the solar cycle, right? It's easy to figure out where solar minimum was after you've long passed it. But as you're moving through it, gosh, is it here? Is it here? Is it here? It's hard to tell. You almost have to wait till you're a year or two out of solar minimum to say, oh, there it was. That's where it was. That's definitively where it was. Same kind of thing with the tidal waves and the earthquakes affecting the ionosphere. Only after the fact can you go back and say, oh, there it is. That's it right there. Outside of that, it's really hard to see because the wiggles are just so tiny. Hopefully that answered that question. Okay. Interestingly, let's see, did I do that? I missed part of it. I see information you share with the public now. If we can just get USGS to step it up, we could have a great world again. Thank you for your show. Yes, don't blame the USGS. The problem is they don't get enough funding. Are you kidding? Congress wants to shut down all the magnetometers on the planet. It's like on USGS. It's like, oh my gosh, we're having to scrape by. So people like Dr. Jeff Love and half a dozen others, they have made it their life, goal to try to keep a lot of these space weather monitors up and running. That's where we come in as a public, right? We raise awareness of space weather. We're able to get things moving, and we are going to be able to get Congress and get people who have the purse strings of our country to understand how important space weather is and how we need to keep certain resources going. So that's where we step in, and I think that this solar cycle is going to be where things are really going to start to change, and space weather is going to take a much higher priority in the eyes of the government than it ever has. And it doesn't have to do with extreme events. We're not talking about the Obama report, the Lloyds of London report. We don't have to go as far as a Carrington class event to get them to realize how important it is to do operational space weather and monitor this stuff all the time. So yes, I'm glad you brought that question up, or that point up about the USGS. Oh shoot, I missed one. Something about the Earth's pole. Each pole, or so one pole gets more. I missed that. Sorry, it scrolled up too fast. If you want to repost that question, feel free. Love to see the full show on just that. I've got so many shows, so many different lectures promised. It really is dictated by my Patreon audience and the ones who support these mini courses. They're the ones that make it happen. So I put out a suggestion of what the topic should be every month, and they respond yay or nay. And some of them, like today, I'm responding directly to Jack asking, he's saying, look, I love this stuff about all the space weather phenomena, but geez, can you do something about a geomagnetic storm? Because I need to know. I'm getting lost in all, well, not lost, but I'm getting, inundated with this stuff, and I know you need to finish these subjects, but he wants to be able to put the full picture together, and I completely understand that. So just mainly for him, but I've gotten that question before by others. That's why I went ahead and tacked on this extra bit, was so that he could scroll through the class and just get to that point and be able to look at that part. That at least hopefully will scratch the itch until I'm able to dedicate a full course to just geomagnetic storms. Well, geomagnetic storms and substorms. I think I'll put them together because they're really important to know the difference. How much of those solar energy are blocked or protected by the Van Allen belt? None. None. Solar, the solar energy, so to speak, as it becomes injected into the Earth's system, is part of the reason why the radiation belts are energized. That's where the energy storage is. So anytime we have a geomagnetic storm, satellite operators start biting their fingernails because, especially in the outer zone, we worry about what we call surface charging, because those Van Allen belts realize that the Earth's magnetic field is kind of like a donut to a great degree, especially in near the Earth where the belts are. And that, if you know what a tokamak looks like, basically a particle accelerator, they look like that magnetically. So our Earth's magnetic shield is shaped exactly the way a particle accelerator is. And so that's exactly what happens. The Earth's magnetic field strengthens, we get particle injections, and then they get accelerated inside the radiation belts, and the energy of the particles inside the radiation belts go up, 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 up. And especially with the electrons, they can cause surface charging, they can cause internal charging, they can cause EMP discharges that then can totally tank a spacecraft. I mean, it can just short the whole thing out. And that has happened more times than we can count. I mean, I can tell you many, many, many different examples where we've had, just from GEO satellites, for example, going out. But we get that also from LEO satellites and MEO satellites as well. There's all sorts of hazards that we have to worry about with particles, especially. Radio communications, we can get like big radio bursts, but those are temporary, right? That's just the sun screaming and blocking, in a sense, jamming our satellite transmissions, jamming from the point of view of just overloading, making more noise than the satellites can overcome to be heard. But that's temporary. That's just noise. It's noise pollution, right? With radiation particles, these energetic particles coming through, and even lower energetic particles coming through, that can actually do permanent damage to spacecraft and electronics, and degrade the spacecraft and take away a lot of its life. And of course, as you notice from what I talked about today, different regimes have different hazards. So a GEO, what survives well in a GEO orbit will not survive well in a LEO orbit, and vice versa. There's a lot to be known about that stuff. So, but that's, again, another lecture for yet another time. So hopefully that answered that question. Okay, ignorance is bliss, yes. Too bad I've got 20 plus years of no bliss. Because of way too much knowledge in space weather and learning more every day. Okay, how weak is our Earth's field right now compared to where we want it to be when more solar storms come with the start of cycle 25? Nah, it's going to be the same. The Earth's field is changing very slowly. Do I think that a weaker magnetic shield is going to cause us any issues? Not ones that are noticeable. Might we get a few more what we call pickup ions, meaning with a weaker shield, might we have more of our atmosphere stripped off? Yeah, okay, maybe. So the oceans will evaporate a little bit, right? But the polar ice caps are melting and they're making more water. So are we going to notice it? No, not at all. I mean, I don't think we'll even be able to sense it. Maybe some of the sensors, the spacecraft instruments that pick up, for instance, atomic oxygen or some of the other evidence of water being stripped off our atmosphere, obviously not coming off as water, coming off as hydrogen and oxygen. But maybe some of those sensors over time will notice maybe a few more, a higher density of oxygen coming off our out of our atmosphere that's being lifted off. But I don't even think we have a time scale capable of seeing that yet. I mean, the space age has only been 50 years, and only within the last 10 or 15 years have we even gotten instrumentation up there to know where to look, what to look for. So, I don't think we'll notice it. I really don't. And as far as how much will that affect when we get hit by a solar storm? Will it cause a bigger storm at Earth? No, likely not. If anything, perhaps the GICs will be weaker, right? So power grids are maybe getting a little bit of a reprieve. As our field weakens, we can't induce really strong currents on the ground. So space, there is an argument that a certain aspect of space weather might actually be lessened by the weakening of the Earth's magnetic field as opposed to strengthened. Once again, space weather really is dictated by what you can see and what region you're in, what you're looking for, and what impact you're expecting. As the Earth's magnetic field weakens, galactic cosmic rays will penetrate more. So we'll have an issue with galactic cosmic ray penetration and issues with aviation more. That will get stronger. But geomagnetically induced currents that could take out our transformers, those will diminish a bit. Everything's kind of a give and take. So there's just not one single answer to that question. Hopefully that at least gives you some input. Okay, I got that. Is there anything with the core that can directly cause radio propagation and disturbances as opposed to ionospheric anomalies? Wow, what a cool question. Well, obviously within the core, it creates our our magnetic dynamo for Earth. So yeah, everything. If our Earth's magnetic dynamo died, we would have we'd only have remnant magnetic field. We'd be very much more like Mars. And therefore, it would totally change how radio propagation works on our planet. We'd have radically different frequencies that we would use. So really, you have to look at the core of Earth as creating a magnetic dynamo being fundamental to everything about radio propagation, at least the main aspect of it. And then, of course, there's all the other stuff that comes up on top of that, which is, the diurnal variations and the layers, the seasonal variations with sporadic E and, tropospheric ducting and all the other kind of stuff, not to mention the gray line. And then we have storms and stuff on top of that, as well as solar cycle variations with solar flux, increasing TEC, all of that kind of thing. But yes, the fundamental aspect of radio propagation at Earth is dictated by our iron core. That really pretty much determines the main set of frequency the regimes that are viable for skywave propagation at Earth. Okay, hopefully that answers that question. If it were only the solar wind in motion, when it hits the magnetic field, then the Earth would get equal charges because the Earth introduced its own motion of the charge. That changes the ratio of particles. I think that's a conversation you're having with someone else because I'm kind of confused. So the Earth gets more electrons at one pole and more ions at the other. Oh, careful. You forget electrons and ions, and maybe I missed it from maybe you had mentioned this earlier. Electrons and ions, they drift in the Earth's magnetic shield in different directions because they're charged differently. They gyrate, they spin around magnetic field in different directions. One goes one way, one goes the other way. So there are, even though we consider most of the near-Earth space and in the solar wind to be quasi-neutral, there are preferential directions that particles move, and that is dictated by the magnetic field. And again, that's beyond the scope of this. So just know that the thing that you're discussing about things going more one direction than the other is even more complicated than you might think. Plus the fact that electrons are so much smaller than protons, than ions, and so they move much more quickly. They can accelerate much more rapidly in a field, in an electric field, or around a magnetic field, than the heavier ions can, because they've got more inertia. So, for instance, that's why aurora, for example, is dominated by electron flow, because electrons can accelerate through a potential difference much faster than protons can. So most of the aurora that we see is not proton, well, even if we could see a proton aurora, most of that aurora that is generated comes from electrons, not from protons. Protons just can't move as fast or accelerate as quickly. So, okay, you answered a ton of my inner questions. Thank you. Oh, good. I'm so glad, Lee. That makes me feel good. Let's see. I'll make it a point to write the president about more funding for USGS. Yes, that would be fantastic. Oh my gosh, I would bow. I'm bowing to you, Eileen. I will bow to you, and anyone else who takes it up to do that, because it's very, very important, and it's becoming so much more important as we become a spacefaring race. We need magnetometers, especially because when this Earth shield wiggles, it dictates pretty much everything. And unless we can read what's going on in the earth shield, from the ground up, when it comes to the ground, we are flying blind. And there's just so much that we need to understand. So yes, absolutely. Please, we have to keep those magnetometers functioning. So thank you. Okay. Yes, likely a Carrington event is inevitable. We had 3 during this last solar cycle. The sun's blowing them off all the time. Just know that we only got clipped by 1 in this past solar cycle. Do we expect to see more in this upcoming solar cycle? Yes, likely. It's a low activity cycle, so yes, we will probably see Carrington class events. Will we get hit by 1? Dunno. Hope not, but maybe. But all we can do, if we can take precautions, then we can ride through it. And there are ways of doing that. I don't think it's as cataclysmic as people make it out to be. I'm not even going to go into the artificial field aspect. Yeah, people want to do that in front of Mars. It's a very cavalier approach, and I don't think it's possible. There's so many things that are wrong with that idea. But a lot of people are talking about that to protect Mars, for example, from solar storms. Oh, geez. Once you do that, you're going to fry a spacecraft. If you could try to put a magnet on a spacecraft, first of all, the spacecraft probably won't function very well. Secondly, you are making that spacecraft as susceptible to solar storms as you make the Earth susceptible. Suddenly a spacecraft that was once flying just fine in space and not really being bothered by solar storms because it didn't really have a big magnetic field that could be jolted and bandied about and dumped energy into, suddenly that spacecraft now has its own magnetic shield, its own magnetosphere. And now all the problems that we see at Earth are now going to happen on this little teeny tiny spacecraft. Yeah, right, like that spacecraft's going to survive. I think it's a very cavalier approach to a very complex problem. So when people tell me that kind of stuff, that's how they're going to solve Mars colonization, I just kind of laugh. Because it's like you have no idea about space weather. This is one other reason why we need to have people understand what space weather is and all the subtleties. Because people think space is empty. And we can do whatever we want up there. No, you can't. It's invisible. All the forces are invisible, but that doesn't mean they're not there. Electric and magnetic forces are not to be trifled with. And they will get you, and they will hurt you. And they're nature doesn't give up its secrets easily, and it doesn't surrender easily. So those kinds of approaches, I think, are need a lot of work. But that's for another discussion. Okay, you guys are making me hoarse. I'm getting so many. Mars needs women. I'm sure David Bowie would agree with that. But he has to find out if there's life on Mars yet. I think his Tesla is still orbiting Mars, right? And there's only one man. It's just the spaceman. He's all alone. We need to send women to Mars to help him out, right? Yeah, where's Iman when you need her? Let's see. But what happens when? What happens when they turn it on? I missed that. Stop messing with other patents. Am I reading that right? Patents when we can't even understand what will help our own. Talk about funding for this stuff so we understand what we're doing first. Lee, that doesn't sound like that was for me. So, all right, okay. I think we're good. So are there any other questions? I'm going to check the Patreon feed one more time to see if anyone has dropped me a question there. Outside of that, you guys have kept me talking for more hours than I care to count. Are we almost at 4 hours? Oh my Lord. This is maybe a record. So you guys have kept me on for a long time. Lee, I do see one more question from you. What can we do to get space weather on the actual media weather channels? I am training meteorologists as we speak. I have 11 meteorologists that have now been trained in one aspect of space weather, at least in the solar phenomena. And these people, a lot of them are going to try to get jobs in broadcast television. So when we have solar storms, it's going to be up to them to fight with their producers to get some airtime for space weather. But they now know how important it is, and they're all raring to go. And every semester I have new students. So, all we can do is just, as one of my students says, I'm cloning myself. And I never looked at it that way, but I was kind of flattered that he said that to me. Because, yeah, I don't want to be doing this when I'm, 60 and 70 years old, and I look like space weather grandma up here. You know, I don't want to be space weather grandma. I want to be able to hand it off to other meteorologists who then can go to different locations and do space weather for their local communities. And that's how we're going to get it on the media channels. But I do guarantee, because I have been on, I've been on the Weather Channel before doing a live forecast, and as the sun begins to ramp up and we start having big solar storms again, I guarantee you they're going to ping me again, and we will see more space weather forecasts being put on the cable channels and hopefully on the local news and broadcast media. But I do have, like on Twitter, for example, I have hundreds of Emmy winning, you know, some of them Emmy winning meteorologists, you know, even chief scientists, chief meteorologists from stations all over the planet, really, who follow me and follow my stuff, and they look for field reporters who are reporting aurora or issues in a region, in their community, and then they will go and contact that field reporter directly, and they will say, hey, can I use your photo? I want to use it on the news tonight. So we're getting there. We're getting there. And I really do think that this solar cycle is the cycle that we're going to see major changes in how the media sees weather and how the public sees weather. So, and it's all thanks to you guys. I mean, I could not have done this if it weren't for you. So, you know, I'm going to keep plodding along, and as long as you keep encouraging me the way you do and keep showing up and learning and then spreading the word, I mean, we are going to make it happen. We are a force now, and we are going to make it happen, and we're going to make it happen the right way. So, you know, I'm just so grateful to you all because of that. So keep staying with me. Yes, I know, get some water. I'm going to rest. 4 hours, too long. Okay, guys. Oh, I just got here. What did I miss? I hate to tell you this, PrevSpec, you've missed everything. I have now, in a few minutes, once I get off here, you're going to be able to rewind and see a 4-hour-long class. That's actually kind of like 2 classes in one. It's all about solar wind, coronal holes, space weather stuff, and then I go into a little bit about geomagnetic storms. So there's a ton of material, plus a great Q&A discussion with the community here, which I just adore you all. Yes, Auspicious Condor, you are a force. Absolutely. Every single one of you are. And I bow to every single one of you. You guys, I just adore you all so much. And thank you for making this so fun. Even after 4 hours with no voice, I'm reluctant to get off because I just love you guys so much, and you've made it so great, just so great to talk with you all. Okay. Yes, PrevSpec, please watch again. Okay. Oh, Mars Needs Woman is a great classic sci-fi movie. Thank you. I didn't know that. I gotta go find it. Is it like a black and white or something? I love those kinds of films. Hopefully it's campy, like, you know, Plan 9, you know, Planet 9 or Plan 9, Catwomen from Outer Space, stuff like that. Mars Needs Women. I'll go look at that up. That's cool. Okay, guys, let me check Patreon one more time to see if anybody else left me anything. I don't think so. I think everybody knows to come onto the YouTube feed. Yeah. So, Joe, you were the only comment. That's good. And I think I've answered everybody who's been on. And thanks, guys, so much for everything. Oh, wait. Auspicious, you have one more. Doc, what is your opinion in regards to plasma and or ether? As if to say, do you believe in the concept of ether? I would have to know a physics definition of that. So I don't really know in what context do you mean, and what is the physical definition of ether spelled with an A? I don't know. I can't say off the top of my head. I can make it a commit either way. I really don't know. So sorry about that. Maybe I'll Google and look up what you mean, or you can send me a link or something to explain exactly what you mean. Because ether means a lot of different things depending upon if you're from if you're in alchemy or if you're a chemist. Ether has 4 or 5 different definitions. So, am I familiar with the Sapphire Project? Yes, I am. I followed as much as I can. I am not actively involved, but I do pay attention every now and again just to see what people are doing. But I have my agenda is slightly different. I'm finishing up doing research in mainstream space weather, but then I'm probably going to focus, once my NASA grants are done, I'm probably going to focus more on full-time developing this space weather broadcasting field, just because it's really, things are really going in that direction, and I think that's where my attention needs to go. So Sapphire, you know, I look into it every now and again to see how things are going, but I don't really do much. I don't actively involve myself with it. Thank you for your knowledge in current sheets and global currents. You're very welcome, Voltaire. I appreciate that. And okay, guys, I think we are done. Jerry, thank you. Everyone appreciates your class, Tamitha, but time to leave. I agree. I am done. Stick a fork in me. Okay, you can tell from my voice. Anybody who knows me. Thanks, Jerry. I appreciate that. And I love you, and take care, guys, and I will see you next month. Okay?